People.
So you're starting another class?
Hello, people.
Good afternoon.
Hello. Good afternoon. Welcome. Oh, got some more people coming in.
I didn't see Marty on the list.
Oh, I think he just joined.
Nice.
Dun, dun, dun.
What you're saying?
Yeah, the notes, yeah. Hello. Oh, wow, look at all these people.
Why is it called quantum indivisible? Now I can't search for Indivisible, which is an organization I belong to.
Oh, yeah, you're right. Yeah, you know, I couldn't remember how to spell indivisible, and I looked it up on Google, and I was reminded of that site. Yeah, totally. How's everybody doing?
How are you doing?
Okay, just a little hot.
Yeah.
Did you hear me when I just spoke?
Maybe. Hello. Yes.
Did you hear the name Victor?
I didn't hear you say it, but I hear you now.
Okay. I just wanted to be sure I was on.
Yeah, totally.
Matt, the previous notes that you uploaded, do they contain any, I haven't looked at them in a while, do they contain what you're going to be speaking about going forward?
Yeah, you know, I spent the last couple weeks kind of like figuring out how to organize all this material, and a lot of it is written out. So when you go on there, you'll see, you know, atoms like 0 through 6 little notebooks. And I mean, there's no way we're gonna get through all that today, but yeah, you know, you can look at it. And I will, been working on like a bibliography of like references and stuff.
What are we going to get to? What do you expect to get to today? Up to spin, or is that later on?
Well, hopefully, yeah, maybe, I guess I was thinking maybe we'd get to start that. We'll see. You know, I was planning on kind of starting, like you'll see that the early, you know, little essays are kind of.
And that relates to platonic shapes?
Aha. Well, you know, there are many connections. And like, you know, in fact, the whole sort of, you know, use of the sphere to represent constellations. I mean, one of the early uses of it was in studying the symmetry groups of like crystals and stuff. Yeah, and actually, you know, we'll see like later on, I don't really go into this in the essays so much, but you know, we'll see how you can represent a spin state as like a constellation. And actually, you know, if you create the constellations corresponding to the platonic solids.
Do the other platonic solids relate to quantum physics, or is it just the sphere?
Well, you know, there are many connections. You know, John Baez has some good little essays about like the platonic solids and stuff. Yeah, we'll see, you know. But I just thought that image was cool.
Oh, yeah.
You know, I mean, it gets at this idea of like, what I thought was interesting about it is, you know, you see the geometrical shapes, but then, you know, inside of them are these images, you know, because one of them's supposed to be like fire and like water and stuff. And it sort of plays at this ambiguity, even when you're reading about ancient atomism, about like whether, you know, they treated them as like little like material particles that just like had those shapes, or if, you know, they were more like Platonic ideas in some way, that this shape somehow is like identical to the notion of like fire or like water or these like elemental things. And, you know, that's in some ways related.
Some of us still believe that.
Hey, you know.
And worse.
Yeah, especially if you play Magic the Gathering cards. Got your mountains, got your plains, you know, give you your mana. Saga continues. All right, well, let's get started. Like, let me share my screen if I remember how to do that. Share screen. Okay, yeah, so as I say, I have a lot of stuff written up. We'll see, how much we can get through. So, when we talked last, I sort of promised like a little treatise on, specifically like the history of philosophy at the end of the 19th century and how it provided, the fertile ground for the development of quantum mechanics with all their arguments about holism versus reductionism. And I realized, as I was putting it together, that there was like a lot of stuff I wanted to say first, just, to give context. And so I decided to take like sort of like a different route. And so what we'll be doing is kind of like investigating what we even mean by an atom. That's sort of going to be our starting place. I have this little epigraph from the Roman poet Catullus. I won't read it, but it's about numbers. You ask how many of your kisses would be more than enough. For me, as many as the stars who, when night is silent, see the secret loves of men. Okay, so, in this essay, when I talk about atoms, I'm not necessarily going to be talking about the periodic table, maybe eventually. Because after all, we know the atoms are divisible, like those atoms, because, we can build an atomic bomb. But the word in Greek obviously means, indivisible, something that can't be split. And, that's an interesting concept. And, sometimes it's characterized by the belief that, like, literally the world is made of tiny little impenetrable pebbles, whizzing around in empty space, perhaps according to Lucretius, we talked about this last time, swerving from time to time in a peak of will. Lucretius writes this famous poem in the Roman times on the nature of things, where he talks about atomism. But more broadly, atomism is the idea that the world is in some sense composed, or can be seen as composed, of indivisible kind of basic atomic elements. We can divide something up, but at some point, the mind decides, we can't divide any longer, and whatever's left is the atoms. And so you can interpret this as like, literally in material sense, like there's tiny little pebbles. But from a more idealistic or idea-based perspective, we can interpret this as a reflection on the fact that when we analyze an idea, what we do is reduce it down to a set of basic concepts fitted together into a kind of jigsaw. There's some certain basic concepts that we have to take for granted, kind of atomically, like axioms. And while an idea can be interpreted in many ways, expressed in different ways as a complex of perhaps different basic concepts, at the end of the day, what it means to analyze an idea is to break it down into basic ideas. Because, that's how we know we understand each other. If we can both reduce our ideas to some basic set of ideas, then we know that we agree. And so I'll say that it's kind of interesting when you think about what materialistic atomism means. In actual practice, the materialist has to reduce all their concepts down to a single set of basic atomic concepts, which are just the concepts of these material particles. And when you put it that way, it seems kind of extravagant. While it's obvious that ideas can be analyzed into atomic ideas, it would really be quite something if all concepts could be reduced to jigsaws made of exactly the same ideas. There's this sort of dream of a set of master concepts from which all other concepts can be derived. It's all just positions and momenta. It's all just this. It's all just, what is the word? It's all just doing, in that sentence. So, I have a little thing here, the materialist could respond to that the real world's made of one set of atoms, but it's only in the mind that we can analyze concepts into seemingly different atomic schemes. But if you're willing to consider that, why not consider the case that it's only in the mind that all concepts can be reduced down to a single set of concepts, your own, whereas in the real world, real things may be able to be reduced down to concepts in different, inequivalent ways. Okay, well, that's a little philosophy. We'll see how it plays out. Because the challenge is, okay, you have this idea, it's whatever, 500 BC, and you want to know, is the world made of atoms or not? So how do you decide? You actually have to try to do it. You have to try to divide the world and our concepts into universal atoms and see what happens. That's a little introduction.
Matthew?
Mm-hmm.
So Andre, hi. Before you go on, can I just make a comment?
Yeah, please.
I don't know how or if you're distinguishing between atoms and particles. And along those lines, when you talk about atoms being indivisible and having position and momentum, you have to remember that in physics, particles, maybe indivisible ones, also have internal properties like mass and charge. And I wonder how that relates to your an analogy with ideas. Do ideas have internal properties?
Yeah, so, it's a great question. I mean, what I'm going to be doing in this essay is I'm going to start with the idea of just a pebble, like the kind of concept of an atom, and slowly layer atop it more and more context until we arrive at like the idea of a quantum, like of a quantum field. And eventually we'll talk about the connection to, the particles such as they exist in physics today. So yeah, we'll definitely get there.
In many ways, the semantic field surrounding an idea or surrounding a semantem is very similar to the nature of the quantum realm. And in fact, you were talking about our ability to convey ideas to one another, to communicate. Jonathan Searle describes when we communicate, let's say a phrase of 11 words, and then each of us has an idea of the semantic field of that word. If I look up the semantic field of that word concretized, there's maybe 11 definitions, but in fact, when you contextualize each word, the word actually appears anew, and all you have in communication is the coinciding of a very small portion of the semantic field of one person with the semantic field of another. You do not have a unity on the idea. It's the same realm of indeterminacy and probability, and the semantic field collapses onto a realm of unity between two people, and therefore communication occurs.
Yeah, I actually really like that. Yeah, I mean, I'm going to sort of push very similar ideas in this essay, that there's like an intimate relationship between, communication and making sure that we reliably communicate, and a lot of the ideas that show up in quantum physics. And yeah, the connections to language are super interesting. Hopefully we'll get to some of that as well. But yeah, thank you. That was a great comment. Okay, so I'm going to proceed kind of, in a way, phenomenologically. So I'm going to start with the idea of an atom, and I'm going to symbolize it with a little dot. Okay, it's just like a little pebble, tiny, hard, impenetrable, point-like. You can turn over a real pebble in your hand. You can split an actual pebble, take a hammer to it. But maybe you imagine splitting it again and again and again, and maybe you can't split it anymore after a while. And we're talking about that pebble. at the bottom in the dust, separated from its fellow dust. Because after all, we're human beings, and we have these bodies or whatever. And whenever we try to understand the world, we're kind of applying concepts that relate to our bodies. We have this sort of idea of like, oh, I can turn this pebble around in my hand, I can move it from place to place. And then we try to apply those ideas that are natural to us to domains which are often unfamiliar. And so, one of the things I want to emphasize, it's like important to try to trace back, where our concepts, arise from. And so in the simplest case, we have a pebble, and what can we do with it? It's just a single pebble. Well, if we had it, we could lose it. We could get rid of it. We could take it away. And so in our little scheme of representation here, we'll denote a pebble with a little black dot, and we'll denote the absence of a pebble with a white dot. And the point of doing that is that we have a way of symbolizing both a thing and its absence. Because that's actually how we perceive it. The empty space there, in your hand is just inviting me to place a pebble in it. To understand, for us, the concept of a pebble is to see the world as one giant set of opportunities to place a pebble somewhere where it's absent, or to take a pebble from where it sits. You can kind of distinguish out of the background of your perception something in the foreground, which is like, a pebble, which might have not been there. To recognize that the pebble is there is to recognize that there's an opportunity to reach out and take it away. It's important to symbolize both the absence of the pebble and the pebble if we want to communicate something with the pebble. Because that's really the relevant thing about, what do you do with a single pebble? It's not that interesting, except for the fact that you can use the pebble to communicate something perhaps totally unrelated to the pebble. I wrote this a couple weeks ago, so you'll see.
So Matthew, would you equate this with Shannon entropy? Shannon information?
If you want to look at it sort of that way, like, in terms of, you have a bit string or something, and you're worried, you're wondering like, how much information can I communicate given some number of bits? Sure, yeah. So, there's a little rock on a ledge by a window, and it's a sign that the riots begin tomorrow. There's a catch. Just the same, we could have prepared a little surprise, which is that it would be precisely the absence of a pebble that would signify the riots begin tomorrow, whereas its presence would have signified regrouping. So in order to communicate something with a pebble, we have to both understand pebbles, to be able to pick them out of the background of our perception, but we also ultimately have to make an arbitrary choice about whether presence or absence is going to be significant, which one we're going to regard as 0, and which one we're going to regard as 1. This choice is completely arbitrary, and yet a choice must be made. So that if we want to communicate with the pebble, we have to both recognize pebble in its absence and agree on which one of those is going to be significant. And what's nice about this is there's a symmetry, which is that, if we swap pebbles for absences, we can on the flip side correct our rule for signifying by swapping them in exactly the same way. So, okay, that's part 1. That's pebble. But, why stop there? You have 1 pebble, why not have 2 pebbles? If there's a pebble sitting there, why not, put another one beside it? And then another pebble, and then another pebble, and then another pebble. And then you have 1, 2, 3, 4, 5 pebbles. There's no limit, seemingly, to our being able to add more pebbles. And we've discovered what it means to count up. And if we can count up, we can count down, removing pebbles until we're back to our original pebble. So now we have this idea of, okay, if we had pebbles, we can have a pile of pebbles. And one way of looking at this is that we're providing, more context for our original pebble. Here's like a little, this is not that important, but here's one kind of nice little way of thinking about it. You could imagine, and this, this is sort of, you might be familiar with Dirac's notion of the Dirac sea, a way of thinking about, matter and antimatter is sort of inspired by this in a much simpler form. You can picture it like our pebbles actually floating in an infinite sea of pebble absences. Each absence represents an opportunity to add another pebble. You can take the bait, add a pebble, flip a white to a black, and again without limit. You can do it without limit. It implies there's always one more absence, no matter how many pebbles you add. And that's perfectly symmetrical to the situation that we started with, where we just had one pebble in a sea of absences. Okay. So what I want to point out at this stage is that, we sort of invented the idea of counting numbers, 1, 2, 3, 4, 5. And when we do that, the point is that we're treating the pebbles in a pile as being indistinguishable, right? We're sort of treating them as if they're all coexisting somehow, simultaneously. Their identity doesn't matter. It's just the fact that there's 3 of them, 4 of them. Are they arranged like this? Are they arranged like that? Doesn't matter. I just care about the number of them. And indeed, that's what it means to number things. To number things is to treat things as indistinguishable, fungible, interchangeable, of the same type in some sense. And, whereas before we had to agree about whether a pebble or an absence would be significant, now we have to agree on what number we start counting from if we want to communicate. Suppose I want to communicate to you the number of birds that flew by my window today. For each bird I see, I put a pebble in a bag. Then I hand the bag to you, and you draw the pebbles out one at a time until there's none left. As many as you counted, that's the number of birds I saw today. But for this to work, we have to agree on pebbles. We got to agree on what it means to put a pebble in a bag and to take it out again. And we also have to agree on what's an empty bag, where it bottoms out. Because after all, we could have, agreed to work with bags that, have at minimum 3 pebbles in them. There's nothing special about choosing the empty bag to be the starting place. And it's important that, just as we can count up, we can count down so that we can communicate the number from one person to another. Okay.
This is Andre. Before you I think it's really important from the point of view of interpretations of quantum mechanics to realize that you had birds, that it wasn't only the counting system, it wasn't only the world that they corresponded to. And if you just had the pebbles, they wouldn't be communicating anything about the world. But you had to assume that there were things in the world that were not numbers to be able to make sense of the model you presented. And this becomes an argument in interpretations of quantum mechanics about what are the, as people in philosophy talk of, what's the furniture of the world that you're modeling with the math. And then some people try, and long tradition of only staying with the math, but it could always be asked, and what's the furniture that they are modeling? And is there a furniture besides the numbers?
Yeah.
But could I add, if it's Michael here, if you assume the pebbles are bits, in other words, binary digits, bits of information, then theoretically you could describe the entire world with these bits. In fact, the entire universe may be nothing more than a quantum computer that computes these bits.
Well, we'll see. I mean, one of the points that I'll make later on is that, at this stage, we're just counting, say, the number of birds, and in doing so, we're treating them as indistinguishable insofar as we want to count them. And, it may turn out when we want to count other kinds of things, we might have to use more advanced and sophisticated kinds of numbers. It may be that counting numbers or bit strings might not be enough to count things. And we'll see that as it.
Well, it should be, according to Shannon.
Well, certainly, if you're communicating, with, like, if you're treating it like, you're communicating with like marks on a page, you're trying to communicate with bits, for example. It's either there, it's not there, and so forth. Then, like Shannon entropy is going to be important and sort of
the
amount of information that you can transfer.
What I should say more precisely is that the universe can be described by quantum bits, not by bits alone, but by quantum bits.
Sure. Yeah. And to get to the previous point, it's there's an interesting question. It's just when we say we describe the world with quantum bits or something, or the world is made of quantum bits. And that's the sort of the drama. How much of the stuff that has to do with how we describe the world, and how much of it has to do with how the world really is. Okay. Section 3, you might even guess where we're going with this. If we started with the pebble and then we got to the counting numbers, now we're going to talk about integers. No, actually, wait, let me just double check something. Make sure I have, just make sure nobody's waiting to come in. Oh, it's true. There was somebody waiting. Returning. Okay. So, if we had a pile of pebbles before, well, now we want, multiple piles of pebbles. We want a bunch of piles. If we can have multiple pebbles, why not have multiple piles, right? But what does it mean, to group pebbles into piles? We could imagine, bringing the pebbles closer and closer together until they're actually in the same place, but that's kind of tricky. So, usually we just signify a grouping that we draw a little circle around the pebbles, make, a little stack of them, put them in a pile. The order of the placement of the pebbles doesn't matter, just the fact that the pebbles are there, there's some number of them, and we can have multiple piles of pebbles lying around. So what can we do with a bunch of piles of pebbles? Well, the most basic thing we could do is we could combine piles, and this is called addition. You have one pile of pebbles, you have another pile of pebbles, you put them together, and you added their numbers. 2 + 3 = 5. And you can think of this as iterating counting up. What we're doing is counting up not one pebble at a time, but counting up by as many pebbles as are in the pile that we're adding, all at once. So we can think of addition as just iterated counting all at once. And naturally, 2 + 3 = 3 + 2 = 5. And if we want an inverse operation, we could count up, count down, we should be able to add and then also subtract, but suddenly we have a problem. Because what if we subtract past 0 to land at what? The negative numbers. 2 - 3 = -1. And suddenly we realize, our idea of number was not adequate. We have to expand our notion of what is a number. And we have to invent negative numbers. And so we can denote those with like a little red dot. And they keep track of our debts. Black pebbles are credits, red pebbles are debts. And there's a rule, which is that if a black pebble and a red pebble are in the same pile together, we can remove them both and we get 0. And in fact, this is how we can define 0. It's any pile with an equal number of black pebbles and red pebbles. black and red pebbles can't coexist in a pile together. And eventually, after all the credits and debts cancel out, the pebbles will either be all red, all black, or zero. And so we have a new kind of freedom in our representation. We could add arbitrary pairs of black and red pebbles, and this won't change the number that it represents. And so what we've done is we've invented the integers and the banking system. Okay. It's a big mistake. All right, anyway. Okay, but why stop there? I call this a dialectic, okay? This is sort of a dialectical unfolding of the concept of number. Go stage by stage, find contradictions, invent new kinds of numbers to resolve those contradictions, and see where it takes us.
Matthew,
Mm-hmm.
I just want to point out that in your introduction of negative numbers, that you needed to at least say something about that when you put that red and black pebble together, you can disappear it. And that it isn't like it just stays around as a zero, because then that introduces the possibility that there are multiple kinds of zero. One black, one red, or two black, two red, and you don't want to do that. So you want to have to add that when you put the black and the red together, they just don't stick around as a zero. They disappear from your.
Yeah, no, absolutely. It's a great point. You know, what I would emphasize about it is so if you interpret this, you kind of ontologically, it's like, yeah, you know, all those, you know, there's just one zero or whatever. But if you interpret it in terms of the scheme of representation, yeah, there's many, many different equivalent zeros. There's the pile with a red and a black, two blacks, two reds, and so forth. And, you know, the fact that there's this freedom in the representation, you know, is really important in the sense that it's sort of the beginning of algebra, in a sense, right? We have an equation, and it's the same equation if we rearrange it, multiply both sides by this, add this to both sides. There's a freedom in our representation, and it's how we use that freedom in order to do things like solve equations. So that perhaps, you know, ontologically, as you're saying, you know, it's all just different descriptions of the same thing, but those different descriptions end up being important in terms of how we actually calculate. Okay. So the saga continues. You know, if we iterated counting up to get addition, we should iterate addition to get multiplication, whose all at once inverse is division. And we're going to get a new notion of number, the rational numbers, which you can think of as being like piles of pebbles. So, you know, if we have two piles of pebbles, A and B, we can multiply them by iterating the addition of A by the number of pebbles in B. So, you know, you could treat this as, you know, 3 copies of 2 pebbles or 2 copies of 3 pebbles. Either way, it ends up with 6 pebbles. And obviously 2 times 3 times 3 times 2 is 6. Okay, cool. Now, at this stage, an important notion arises out of the interplay of addition and multiplication, and it's the prime numbers who play a starring role in mathematics, okay, right? A prime number is divisible only by itself or 1, so that whereas 12 is 2 times 2 times 3, 7 is just 7 times 1. And yes.
How do we prove that 2 times 3 is equal to 3 times 2?
Well,
Wise ass.
yeah, you could just look at this picture. I mean, if you
Who is
were
that,
being able
Victor?
to turn this at 90 degrees as a proof, then, you know, there you go.
Well, I'm sorry. I was distracted, I think, by Victor. What was the answer? I'm not trying to be a wise ass.
No, no, no.
You know, this is the whole basis of what we're talking about.
Yeah, right. So I mean, whenever you talk about a proof, right? It's what do you accept as the basic elements that you're going to assume, and then you're going to prove the statement in terms of those things. So, like for example, I have this picture here where you can see, well, you can make a rectangle out of 2 times 3 and a rectangle out of 3 times 2, and it's the same number of pebbles. It's the same shape. Turn 90 degrees.
Well, that's easy. But in general, how do we prove that n times m is equal to m times n?
It seems like you define this as sort of an operation, right? Where you twice add this what's in the set containing 3, or you can 3 times add what's in the set containing 2, and you can, if your rule is just count how many you end up with, then if that satisfies.
But how do you count as, you know, n and m are very large numbers? It's easy to do it for 2 times 3, 3 times 2, but
Yeah, I see.
just in general, how do we know that's true?
Maybe you formalize it all in set theory and then turn the crank. I'm sure.
Yeah, I thought there might be an easy explanation. I know that, you know, it can be done, but
I'm sure there's like an abstract French proof that runs to it's about exactly.
stop beating up on the French. They got enough problems.
Matthew, I think your initial step is a valid way to say it's a proof that you introduced 2 times 3 and you didn't introduce it from saying, oh, you had to keep your head this way or that way, and therefore looking at it from moving your head is the same as actively moving the rectangle, and that's the proof. The proof.
Let me reformulate, Andre. Let me reformulate the question. How do we know that multiplication is commutative?
Yeah, and what he just gave you was a proof that multiplication is commutative for whole numbers.
The 2 times 3 for n times m.
It might be more illuminating to consider the cases where we can prove that multiplication, you know, isn't commutative. But to do that, you know, there's going to be, you know, some more structure.
I apologize.
No, it's a fair question. I mean, because, you know, after all, it's like, what do we even mean by a proof? This is in some ways what we're talking about.
No, but what makes intuitive sense and what is actual could be completely different.
And that's where all the good stuff is.
What's that?
So that's where all the good stuff is.
Yeah.
So there's an infinite number of primes. I won't go into the proof exactly, but, you know, it was known to Euclid. Well, actually, no, I will. Sorry. I will go into the proof of that. I won't go into the proof that a whole number can be uniquely broken down into a set of prime numbers, just because, you know, the proof isn't that hard, but it's like a little technically annoying. But I do have here a proof that there's an infinite number of primes. Okay, it goes like this. Every second number is divisible by 2. Every third number is divisible by 3. Every fourth number is divisible by 4, and so on. And what follows from that is if we add 1 to any number, it won't be divisible by any of its old primes. You know, for example, 14 is 2 times 7, and 15 is 3 times 5. And if you think about it sort of musically, 14 falls on the beat of 2 and 7. And if every second number is divisible by 2, every seventh number divisible by 7, both beats fall on 14. But if we add 1 to 14, the resulting number can't fall on the second beat or the 7th beat because it's been displaced by 1. And this is a general rule. So then you suppose there is a largest prime number. Well, you could take that prime and all the primes less than it, multiply them all together and add 1. That number couldn't be divisible by any of our known primes, so it must contain a larger prime number within it. Hence, our initial assumption has led to a contradiction. And if you assume the law of the excluded middle, the converse is true. There are an infinite number of prime numbers. So it's cool that we can take a number and break it down uniquely into a product of primes. And that suggests the following idea, why not introduce an infinite number of colored pebbles, one for each prime? Pebbles signify the prime. So, black is 1. Okay, is 1 a prime number? It's a hot button issue. 2 is green, 3 is blue, 5 is orange, etc. And so then we could write 12 like a little pile like this, a little 2 pebble, a little 2 pebble, a little 3 pebble. But now our rule is different. We can think of these colored pebbles as secretly under the hood being like piles of pebbles. And, we could formalize this by being like, well, when a bunch of piles of pebbles are in a pile together, we multiply them. We don't add them. So we have a new kind of pile, a pile of prime numbers. And the rule is we multiply elements in a pile of primes together to form a composite. And the analogy is kind of nice because, just as our original pebbles coexisted unordered in an additive pile, the prime pebbles coexist unordered in a multiplicative pile. So, at this stage, we could interpret, the primes as being like our new atoms. And, multiplication becomes trivial. You're just like, 4 times 5, you got 2 greens and an orange and you stick them together in a pile.
But how do we go backwards? How do we know if a number is prime? That's the problem.
Right, so you gotta go, ultimately, in the worst case, try dividing your number by all the primes in turn, see what you got, It's this important point, right? So it's easy to multiply. It's hard to go through and break the numbers down into their primes, leading to various now outdated cryptographic schemes. But we have a problem, just as before, we subtracted past 0 and suddenly had to invent negative numbers. We have this problem, what if we try to do something totally crazy like divide 3 by 2? There's no counting number such that, n times 2 equals 3. But if we can multiply, we have to be able to divide, because that's the game we're playing. And so we just introduce a new kind of number, a rational number. And so we interpret 3 over 2 as a fraction. And, in terms of pebbles, if you like, we could think about it like introducing a little inverse pebble here for each of our primes. I got like a 1/3 pebble and a 1/5 pebble. And just like the rule for the blacks and the reds before, it's like if you have a 2 and a half pebble in the same pile, it's a 1. Classic. So if a prime pebble and its inverse appear in a pile together, we can remove them both. We can add as many 1 pebbles to a pile as we like, multiply by 1. Multiply by 1 doesn't change the number. Moreover,
I'm wondering, maybe I missed the notation point, but why that isn't 2.5? Well, like what makes in the notation distinguishes that as a multiplication versus a set containing a 2 and an inverse 2?
Just because they're colored.
Colored is being multiplied?
Yeah.
Okay.
Yeah.
They are chromodynamic, QED.
Yeah, totally.
No.
Marty knows. So similarly, we have a freedom in our representation, right? We can add pairs of prime pebbles and their inverses, and the pile will still represent the same number. And when all the cancellations have taken place, we have reduced the rational number to lowest terms. And as I was saying before, you might be like, oh, well, that's a problem. There's redundancy in our representation. But actually, it's pretty useful if you want to add rational numbers, If you want to add a 5th and 2/3, you got to find a common denominator, 15, and then you can just add the numerators. It's kind of nice. Our negative 1 pebble still hanging around. Okay. So, if integers can keep track of credits and debts, which is related to the ability to arbitrarily decide what we're going to regard as like 0, and positive is this way and negative is that way, rational numbers allow us to keep track of different denominations. Our ability to arbitrarily decide what to regard as one. You know, for instance, I have a ruler, and I measure something in terms of that ruler to be 3 units, but you have a ruler B, and each unit of your ruler is worth 2 of mine. And we could describe this relationship between our rulers with a rational number. And so, you know, if I was trying to calculate what you would measure the same object to be in terms of your ruler, I would just multiply the answer I got by a half and get 3/2.
The old ruler, the dollar, is about to be replaced by the yuan.
Yeah, and yet, you
Or
know,
pebbles.
representation matters. So yeah, exactly. I mean, rational numbers allow us to switch between different currencies, exchange rate between gold and silver, dollars to yen, hours to minutes, so that, you know, if we want to communicate a number at this stage, you know, we got to provide context. What are our different units? How much of your one is there per my one? Here's a little picture. I think this is like a woodcut from the Middle Ages. It sort of tells the story of Pythagoras discovering how music is based around numbers and ratios. So, you know, he famously, so you see people here, he's got some little water glasses filled with, you know, different amounts of water. He's got some bells, you know, different size and weight. He's got flutes, you know, with different lengths. He's got strings that are of the same length, but, you know, under different amounts of tension. And each one of these is numbered.
Question: is it, to your knowledge, is it Pythagoras who figured out that the harmonic of a note is the same note at a higher octave?
You know, like Jesus.
Is this just allegorical?
Yeah, right. So like Jesus, it's like, did Pythagoras really? I mean, I don't know. But even in the ancient world, I mean, the Greeks were all like, yeah, I mean, that was Pythagoras, you know, famously. And, you know.
I had a roommate once who could hear a car go by and tell you within the note of the car, he could hear each of the harmonics, and he could go up 5 octaves in his head. That's how good his perfect pitch was. He could tell you which harmonics within 5 octaves were missing. I am not joking.
That's amazing.
Was he become like an auto mechanic eventually?
Yeah, you're really diagnose a car.
He was a jazz musician.
From over the phone. Yeah.
He was a jazz musician with the most perfect pitch I have ever encountered.
Wow.
That's incredible. I mean, I've known some people with perfect pitch. I mean, the irony, of course, is that, you know, they will often get pissed off if, like, you know, something's been modulated into a different key, or if the recording's playing a hair slow, and, you know, because they're sensitive to the actual, you know, most people just pay attention to the relative pitches, but they're like, oh my God, you know, this is like literally supposed to be an A flat. That's really.
Well, you know, Victor, you know, a physical object has a natural resonant frequency, including all of its harmonics, but the harmonics generally taper off at the higher end, not intermediate. So I'm not sure I understand what you meant by that. In other words, he could tell the primary frequency, and if double and triple were missing, he would know that. It's usually the higher ones.
With each octave, you have more. You actually have more harmonics. You start with the with an A, and then you get an A, and then you get a fifth, and then you get an A, and then you get a third, a fifth, and a seventh, and A, and it just actually the harmonics start increasing as you go up. That's how it works.
Yeah, and the different, you know, timbres of a given instrument have to do with the kinds of, you know, frequencies that dominate in the signal.
Yes, the relationship among the harmonics, but the harmonics generally taper off as n gets larger.
You know, it sort of has to do with the stiffness of the string, for example. Like if it's a vibrating string, you know, it's going to have a certain stiffness, and so it's not going to be able to vibrate at, you know, at like a sufficiently high frequency. Yeah, totally. So yeah, I mean, you know, I had to mention Pythagoras and the myths associated with him, who believed, you know, that, you know, all things were number, that ratios governed the world. And yes, legend is that, you know, he investigated the mathematics of, for example, a plucked string. You know, you consider a guitar string, you know, you divide it. I have a guitar, I bring it over here. You know, you divide the string in two and you play a note, you get a note twice the frequency, an octave higher. You know, divide the string at the 7th fret, you know, you're dividing it into 3/2, you hear, you know, 2/3 times, or maybe it's the reciprocal, whatever. As we were saying, the different ratios correspond to the familiar musical intervals. So, you know, 3/2 is like a fifth. You know, 3/4 is a fourth. 5/4, you know, has to do with the major third, and so on and so forth. And so you see, you get like this most basic musical thing, you know, like the major chord, just from considering, you know, the first 3 primes, 2, 3, and 5. And, you know, strings whose lengths are related by these like low integer ratios harmonize. And so this is what Pythagoras was into. He was like, wow, it's kind of interesting. Okay. All right, so now we're gonna do a little musical experiment. So I'm bringing this up to motivate the following thing. You know, and this is related, you know, in the end to quantum mechanics, right? So when you hear a musical chord, we hear it, you know, in terms of the notes within it. You know, I mean, we can be more sophisticated about that the more, you know, trained at music we are, but, you know, just as like we can decompose a number into its primes, we can decompose a musical chord into its constituent notes. You know, and the physics of this is like, you may or may not know that there's like a little array of tiny little bones of different length in your ear. And when the sound wave hits those bones, the bones of different length vibrate, you know, sympathetically to the different, you know, harmonics that are in the signal.
That's not true.
It's not true?
That's not true. It's not the little hairs vibrating that give you the tones.
Or little bones.
What vibrates is the liquid in the what's it, cochlea.
Oh, okay. Well, all right. So maybe there's some more specifics.
Yeah.
But yeah, I mean, ultimately, it's like you can get the same effect with, like, you know, you put a bunch of tuning forks, you know, in front of you that make different notes, you know, and you can play like a loud chord. And then you stop and you hear, you know, oh, you played a major third, the tuning fork that's tuned to, you know, C, E, and G will be particularly loud and resonant afterwards.
There's nothing that's resonating, though. It's the thickness of the cochlea at the spot. All the hairs have they're roughly the same size, and it doesn't matter what their size is.
Oh, okay, maybe I'm completely wrong. I might be working with outdated or obsolete information. Never mind. Well, we'll look it up. I'll get back.
Ask him a simpler question about what a note is, because I know what a frequency is, but I'm not sure if we're talking about notes as just another word for frequency, or
yeah, I mean it like
notes are more like composite packages of various frequencies coming out of an instrument. Yeah.
In this case, yeah, think about a note as just like a sine wave at one frequency.
Okay.
So, you know, and this is related to, you know, the idea of a Fourier transform, that you can decompose like a periodic signal into a sum of sine waves of frequencies 1, 2, 3, with a certain amplitude for each of those, and maybe their phase shifted a little bit. I won't go into this part of the math too much now, because we're still just talking about rational numbers, not, you know. But so anyway, one cool thing is like, okay, so we can generate some music with Python here. So for example, this generates a sine wave of a given frequency and amplitude. This layers a bunch of notes on top of each other, make a chord. This concatenates a bunch of chords to make a melody, and then we can play it. So we can just see here, an A is frequency 440, standardly. And then we'll get a little D flat and an E. And you notice it's just the frequency times 5/4, and E is the frequency times 3/2. And it's like it's not the most pleasing sound, but there you go. You hear it, it's the chord. Okay.
Matt,
Mhm.
I would just add, as an electrical engineer who has studied this extensively, I would add that any waveform, even a non-periodic waveform, can be decomposed into its frequency components by Fourier analysis, albeit they be an infinite number of frequency components. But you cannot do the same thing with factoring a number
Right,
into
I see what you're saying.
primes.
Yeah, okay.
So the comparison is a little misdirected.
Sure.
You can always analyze a signal, exactly, but you can't decompose a number into its primes.
Well, not easily. But
Not usually.
and
There's
not in
no
practice, but in
automatic
principle, you
way to
always
do it.
can.
I mean, Shor's algorithm, I guess, is it Shor's
You're
algorithm?
talking about as a practical operation. It's not doable.
Yeah. Whereas
Theoretically, it's always
Whereas Fourier analysis is exact. You can always decompose any waveform, periodic or non-periodic.
Right. Well, I mean, there's some subtlety, involving, later on, I was going to try to talk about like wavelets, like a little bit. I mean,
wavelet.
it's an interesting issue, right? Because it's like you have some function defined. It's one thing if the function's defined on a certain interval, and then you can, break it into a Fourier series like over that interval, and then you have these situations where, there's like a sort of, it's defined over an infinite domain, and I mean, there's like a lot of interesting.
Well, that's only for periodic. For a periodic waveform, you have to assume an infinite domain, but you could have a pulse,
right,
which is over a finite domain, and you can still analyze it with Fourier analysis. It would be a continuous rather than a discrete. In other words, instead of having harmonics, you would have every single frequency would have an amplitude.
Yeah.
Of some sort.
But we will, when we get to a later section, when we talk about, position and momentum in quantum mechanics, we'll use, like that kind of Fourier transform. Yeah, totally.
Absolutely, and that's what quantum mechanics is about. That's also what Heisenberg's uncertainty principle is about. It's really a Fourier analysis.
Absolutely. It's if you hear a note, it might be 440, but if you only hear it for like a microsecond, you're not going to be able to distinguish what is the frequency of that note. You have to listen to a note over a certain interval in order to distinguish what frequency it is. And that's in some ways just like Heisenberg's uncertainty principle. Yeah, absolutely. In the case of the vibrating string, a string, like we're sort of saying, it doesn't just vibrate at a single frequency, but many of them. There's all these harmonics, and it sort of makes visual sense. You can imagine, the string vibrating up and down, and then kind of, divided in the middle and divided into thirds, and there's these different nodes, places of no motion, and you can sort of divvy up the signal into these different components. And here I have a little thing here. We can listen to the harmonics of, such as would be like in a vibrating string. I don't know how well that came through, but you hear the early harmonics are rather consonant, and the higher ones are a little more dissonant, and this is what Pythagoras was noticing.
I remember reading. I never tested it myself, but in my hobby as like vacuum tube audio amplifier type stuff, that the good harmonics are even, like pleasing harmonics are even, and odd harmonics are unpleasant. So like if you're trying to tinker with a circuit to You know, like the higher quality audio amplifiers are the ones that have removed the odd harmonics, you know.
Well, that's sort of related to like the, like, what is it? Like a clarinet, you know, has its sound. What is that? It's like mainly odd harmonics.
Yes, it's odd.
Yeah.
Piano is even, and flute is practically a sine wave.
I think it's like odd are considered sort of harsh, and even are considered sort of, I don't know.
Sure. I mean, I think about it more like nasally. The odd ones are.
Odds are nasal. Okay.
It depends on what. Yeah.
We hear the difference between consonance and dissonance in the various harmonics because we use a tempered system, which is not used in all the other musical traditions. They use an acoustic system, and so what we call a dissonance in other cultures is not a dissonance within harmonics.
You mean what is pleasing to an individual is culturally influenced?
Yes.
Yeah, it's the well-tempered clavier. It's the beginning of temperament in Western music, right? That stratifies and hierarchizes everything, and it eliminates the noise, what we now hear as noise patterns.
Yeah, and it's actually, when you hear, if you go listen to a recording of like Bach or something, played on, period instruments where they're using the just intonation or whatever, it's kind of disconcerting. You're not used to hearing, like literally 3/2, because now we divide up the interval. Like even temperament is you take the 12th root of 2, and the interval between each note progressively on the piano is basically a 12th root of 2, which allows you to play music in any key and have it sound more or less good. Which incidentally, puts into context a lot of, it's often weird reading like ancient and medieval writing about music because they're very like interested in talking about like how like different, basically like keys have like different feelings and stuff like that. It's easier to understand when you realize they sort of were working with these tunings where, if you've tuned it, so that like the ratios are nice, for C major, and you start trying to play something in E major, it's going to sound a little off. Kind of interesting.
But is this true like very broadly or just talking about like relative to what we have as our typical examples from Western music, like variations from that are slight are, the fact that we don't like them as much is cultural, or is it like a shrieking down? There's a culture somewhere that loves that.
So, I mean, different cultures, like in the Middle East, I mean, they love microtones. They're always like wiggling around notes, using sort of chromatics, all sorts of weird stuff that, Western music doesn't use as much. I mean, if you take it to its logical extent, there's the famous, composer Arnold Schoenberg, who in, the early 20th century was like, aha, I've seen a progression in Western music. Look back at, medieval to, whatever, Baroque to, classical to romantic. And it's like, and then you get Wagner, and next thing you know, we're using more and more harmonics, higher and higher harmonics. And maybe music is getting to a place where, all 12 notes of the scale would be treated evenly and equally, and consonance and dissonance is all just completely culturally determined. And he based his entire career on that idea. And one thing you can say about it is that if you listen to his music, it still sounds pretty fucking crazy, what I mean, to this day. So, but at the same time, if you look at the popular music of the 20th century, things like jazz and, ultimately rock and roll, like influenced by jazz. I mean, the kinds of chords and patterns which are accessible and, in popular music, increased dramatically in the 20th century, so it is sort of true.
But of course, jazz and rock and roll are greatly influenced by African music.
Oh, yes.
And other than Western musical scales, I mean, Asian and African scales are different.
Yeah, well, although the other thing is it's sort of I think of it kind of like a hybrid, because I mean, okay, like in the 1920s, like you can go listen to some French Impressionism, you know, Debussy and like Ravel, and then you go listen to, you know, the jazz of the time as it's evolving and stuff. And they're incorporating some of the same stuff. I mean, a lot of jazz musicians, you know, headed to Paris. And I think there was just like a lot of, you know, cross-cultural exchange that was going on. But yeah, like absolutely. I mean, it's, you know.
I was talking about something different. When you're talking about dissonance consonance, I was talking about dissonance consonance within the harmonic series and dissonance consonance within the scale series in a tempered system and an untempered acoustic system. That's completely different. I mean, in the 20th century, everything is done in Western music. Every possibility,
Yeah, every possible thing
is explored. And so, yeah. But I was talking about acoustic dissonance versus tempered dissonance. Okay.
Yeah, totally. Yeah. Yeah, it's interesting. You know, my friend Jeremy reprogrammed his piano to use, you know, the Pythagorean tuning, and it was quite fun to play around with. Okay, so moving on a little bit. This is not important. This is more like a preview of stuff to come. But, you know, just, you know, if you're wondering, you know, I threw up some partial differential equations. Like here's a little wave equation. You know, you can solve it. You could separate some variables. You know, I won't go into this whole thing. But, you know, the upshot is that, you know, you can solve this equation here and show that it has an infinite number of solutions, one for each of a countable number of so-called eigenvalues, which are basically the frequencies. And the associated eigenfunctions are these little sine waves. And, you know, so solutions to the wave equation, you know, there's an infinite number of them, and you can add any number of these solutions and get another solution. And the counting numbers appear here because, you know, because of the boundary conditions of the string. You know, you can play around with this, add a damping term, you know, since obviously you pluck a string in real life, it doesn't go on ringing forever. And okay, another digression, like while we're here, it's great talking about music and stuff. It's the case that if you, you know, have the length of a string, you double the frequency, but you have to apply 4 times the tension to double the frequency. So, you know, so when you're tightening the string, you're in a guitar, you're adjusting the tension. And I just, like, I have to mention this because it's like, I don't know if it's like that widely known, but, you know, a couple of years ago, I realized they put Isaac Newton's papers, many of them, online. And it's very entertaining to read them. He's writing about math and history and theology and all sorts of stuff. And he was, like many Renaissance thinkers, you know, these guys didn't think of discovery in the same way we do, because they had been confronted with, you know, what had happened, you know, was like the Byzantine Empire falls, I forget, like the Mongols are sacking Baghdad, and the libraries get fucked up. The books in them start migrating around, you know, and, you know, this sort of sets the stage for the beginning of the Renaissance, where people discover, holy crap, you know, there's all this literature and science and stuff from the ancient world that we didn't know about. And so at this time, you know, people didn't know what people knew about in the past. And so when they would like discover stuff, they would often sort of frame it as like, we've rediscovered something that was lost. You know, there's always like a kind of a default assumption that, well, like the ancients must have known about this. And so I'm really kind of decoding or recovering what these ancient people knew about rather than just merely discovering it myself. And the thing is, in actual practice, you know, this proved to be an inspiration to them, right? It's like they were kind of, like their process was, you know, to read a bunch of ancient texts and like think about what they could have meant. And so Newton actually thought, this is a bit of a simplification, but Newton basically thought that, the Pythagoreans knew about gravity, but just kept it a secret. I mean, because that was the famous thing about the Pythagoreans. Their esoteric, cult-like, nature or whatever, they would have famous passwords, some of which survive today. Can't remember any of them right now. Something like, what is the tier of Cronus? And you answer like, the moon, or something like that, and they let you in. Or there's this idea that, not all of their secrets were divulged.
But the thing is, Matthew, the ancients could not equate the orbits of the planets with the reason that we stick to the surface of the Earth. I mean, it took Newton to figure that out.
Here's Newton's reasoning. Like, this is why he thought the Pythagoreans probably knew about gravity. It's kind of an interesting argument. So really, you actually have to imagine that Newton's kind of imagining that like the planets are all connected by strings. Like, I think this is like underlying like the thing where he's like sort of like, I make no hypothesis about like, how gravity is like actually transmitted. He's sort of keeping it secret. Like, he's kind of thinking about it like the planets are connected by strings, right? So here's the argument, right?
Well, he believed in instantaneous reaction. It took Einstein.
Well, I think Newton was sort of like, I'm not gonna go out on a limb and say. I think like the Newtonians, sort of philosophized about it and tried to decide how okay they were with, instantaneous action at a distance. And after all, even before Einstein, when, in the 1700s, 1800s, they like
a spooky idea, one might say.
Absolutely, yeah. But, even before all that, I mean, you can reformulate, gravity as like a kind of potential equation. And, you don't necessarily have to think about it like one mass is instantly affecting another one, but that there's like some field or whatever, like mediating it. But that sort of comes later. Okay, so Newton says F equals ma, great, and that the force due to gravity is basically, the mass of the one times the mass of the other over the distance squared. So if you work it out, for the acceleration of the first mass is the mass of the second over the distance squared. And I'll notice you get the same acceleration if you have the distance, which gives a note twice as high, or if you multiply the mass or tension by 4. So there's like, for the frequency of a string, it's given by the square root of the tension over the length. So if you square that, it just says frequency squared is equal tension over length squared, which is just the law for gravity. So it's sort of like he's making an analogy, actually, that acceleration is kind of like frequency squared. Now, he didn't, like this was like not his public argument, right? Like, I mean, I think he even gave the argument that, the weakness of gravity, like you imagine it like the gravitational force is getting proportioned out over the surface of a sphere, whose radius is the distance. And, the surface area of the sphere is, 4 pi r squared. And so you get that squared term. But I think it's kind of funny.
Are you saying that in his imagining of planets being connected by strings, those strings are vibrating like notes?
Yeah.
Saying, and it's the same, that's the relationship between the harmonics and tension and gravity and
I think that's sort of, I'm not saying like that's what he ultimately like decided on, but like when I imagine how Newton discovered gravity, it wasn't so much sitting outside getting the apple to fall on his head. It was like reading these ancient texts about Pythagoreanism. And
but does he talk in some paper about in one discussion or one piece simultaneously talking about notes and gravity?
Does he talk about the music of the spheres specifically?
Yeah, I mean, everyone loved the music of the spheres, which is interpreted in a lot of different ways, right? Like, I mean, at the basic level, it's like the planets go around in these cycles and be like, for every X number of, Mercury, you know, Venus comes up or something. And so, you know, the Pythagoreans were like, it's ratios, like just like music, you know, is governed by these ratios, you know, the cycles of the stars and planets are governed by these ratios. And, you know, that idea like is elaborated in like lots of different forms.
But you should, but Matthew, you should add that they were completely wrong because they believed in a geocentric universe rather than a heliocentric solar system. So they had cycles, but they were they couldn't explain them.
Yeah.
That is not so. There's a number of ancients that understood that our star system was heliocentric.
Yeah, it's true. There are some ancient philosophers who you know hold a heliocentric view. I think the best way of treating it is like it probably was a rather common belief that the Earth was in the center of the universe, especially for someone like Aristotle, where you know his idea is that you know you have earth, air, water, fire, whatever, and it's in the nature of things to like all kind of return to their center. And so, you know, all the earth is kind of trying to like attract all the other earth. And so it like forms this core, and then like the water is trying to get to the water, but the earth's there. And so the water is like forms a layer atop the earth, and then the air, and then the fire.
Well, what it is, it's about the egocentricity of human beings to believe that they are the center of the universe.
Yeah, well, so that's a classic Enlightenment meme. You know, I mean, that's, you know, it's really true. You know, it's like starting in the 1700s, people start saying that. And I think it's fair to say, you know, but to give, you know, the due respect to the cleverness of the ancients, I think it was, you know, like even if a lot of people thought that, you know, we were in the center of the universe, it's like, it was a point of disagreement. Like you had, you know, people argue on both sides.
There was not just Aristarchus. I mean, there was an understanding of it to the degree that the librarian of the Library of Alexandria was able to measure with a rather astonishing degree of precision the distance between the Earth and the Sun.
Yeah, it's true. And, you know, just a random point, you know, one of the other denizens of the Library of Alexandria was the poet Callimachus, who I just mentioned because at the beginning I had this little poem by Catullus. And Callimachus was actually Catullus's favorite poet. Small world. Anyway, and it happened around, Callimachus was more or less contemporary with, I forget what his name was, the librarian at the time. But, okay, well, here's a fun thing, another musical thing. Let's hear what it sounds like to count, right? Like if every second number is divisible by 2, every third number is divisible by 3, and so forth. We could play this game where we start counting, and for each number, we break it down into its primes, and then hear a chord formed of sine waves. So for example, for 12, you would hear a chord of, you know, frequency 2, an amplitude 2, because there's 2 of them, and a sine wave of frequency 3. So, you know, we can kind of convert composite numbers into chords, and then hear what that sounds like. And it's cool because, like, if you think about it, this is like all possible rhythms and harmonies overlaid atop each other, going on for infinity. And it does in fact sound like some pretty crazy jazz after a while. Yeah, you know, every second beat, you're hearing the 2. Every third beat, you're hearing the 3. Every fifth beat, you're hearing the 5. Every seventh beat, the 7, and so forth.
Matthew, are those beat frequencies?
Oh, say that again?
The peaks that we hear, are those what you would consider beat frequencies? If you know what a beat frequency is.
Right, yeah, the 2 frequencies at very close to each other.
And they're getting more and more spaced out over time?
Yeah, I mean, one thing is that, you know, the way I do it, like the pitches get very high kind of quickly. And so there's a little distortion in the upper registers.
Can you scroll up just a little bit just to see the code?
Oh yeah. So we got a little thing that generates the note, like a sine wave, as like a NumPy array, given the note and amplitude that you want, frequency. This, sticks a bunch of notes together into a chord.
What's happening with each iteration when we hear a different sound?
Yeah, so what it does is right here, it counts from 1 to 100. It finds the prime factors. Well, actually, I should mention, it doesn't just do the prime factors, because that sounds cool, but like less cool than this, which is it finds like all the factors. So like for 12, you'd actually hear, 2, 3, 4, 6, and 12. Just nicer. So is that even true? Yes, I think so. Maybe not, whatever, doesn't matter. You could do either one, but yeah, it just counts, breaks the number into its primes, creates a chord, and
the chord is composed of some base frequency multiplied by the factors?
Yeah, totally, right. So the base frequency is just there because, there's a limit to human hearing. And so, if you just hear frequencies of 2 and 5, you wouldn't be able to hear it.
I didn't even mean to.
We'd scale it up.
I didn't see that you actually named a variable base frequency.
Yeah, totally. And, you can play around with this, hear just the prime factors, all the factors, change the base frequency, change the note duration. I've tried like that. There's many different things that I've done that all sound kind of interesting.
Sounded like a calliope playing a jazzed up version of Phil Glass in the Middle Ages.
Yeah, I'm gonna quote you on that. Yeah, totally. That's the vibe.
So Matthew, is there a way to reverse this and factor a number into its primes?
Or hear a sound. Yeah, I mean, why not? Yeah, totally, you could do that.
So, you could win the Millennial Prize.
Hey.
Why are you wasting your time lecturing us?
I mean, it brings up this point, which is like when I first started doing this prime number music, which must have been back in 2013, I sort of was approaching it from the mindset of like, I don't know how people solve fancy math problems and stuff, but, I can hear math by using my computer to like generate math, like music that's like based on it. I was like, if I just listen to this long enough, it'll just get into my unconscious mind and, whatever. So maybe it worked. Hard to know. So, and then I just have another little digression here about like, what we talked about before, really, right? It's easy to multiply primes together. It's hard to break a number into its primes. Furthermore, it's like one consequence of this is like if you're counting along, it's kind of surprising where the prime numbers appear. And this is like a famous problem trying to like predict, the distribution of prime numbers. One could talk about the Riemann hypothesis. There's a famous prime number theorem that says, for large n, the probability that a random number is prime is about 1 over log n. And, that's a whole interesting thing too.
I'm sorry, 1 over log n in what units?
Where n is the integer that it's like the number primes less than n. So like the percentage of, like, given some large n, like what's the probability that a randomly selected number from 1 to n is prime? And it goes like 1 over log n. So, I mean, all it's really saying is like, as we well know, it's like the primes get more spaced out as you go on because, the primes can only fit in the slots that are left over from like 2, every second number, then every 3, and every 5. And then there's gonna be these like gaps that have to be filled in with new primes. And like, as you count more and more, I mean, there's so many cycles that you've opened up that it's like.
Is this prime number theorem derived from the Riemannian hypothesis?
it's not derived from it, but it comes out of the same world. And I mean, it was proved, after Riemann. I mean, it was proved at the end of the 19th century.
But the Riemann hypothesis has not been proved.
Yeah, the prime number theorem, I don't think depends on the Riemann hypothesis. This is just sort of like a general statement, you could argue. The Riemann hypothesis is literally saying that the zeros of the Riemann zeta function allow you to literally predict exactly where the primes will be. And that's a much stronger statement. Okay, but there's a whole other thing. Okay, if there's more thoughts about music and prime numbers, we're gonna take a little detour from that, because there's something we haven't thought about. Oh wait, one of those things includes someone who I have to admit into the meeting. Okay, there we go. What happens if we divide by 0? We want to be able to add, subtract, multiply, and divide our numbers. We should be able to divide by 0. I mean, what happens then? So just as, we try to divide 2 by 3 and realize we need to, expand our notion of numbers, we can do that again. So there's a multiplicative inverse of you see here, we could just treat 1 over 0 as a so-called infinity and 1 over infinity as 0. But notice that negative 1 over infinity should kind of also be 0, since there's no difference between negative 0 and 0. So one way of thinking about this is like this, for example. We can do a 2-dimensional stereographic projection. We imagine all the rational numbers on this line. And we imagine, that there's a circle here. And we're sitting at the top of the circle, and we're pointing to each of those numbers on the line. And this uniquely maps, each of the rational numbers on the line to a point on the circle, and then there's an extra point left over, and it's the so-called point at infinity. So we'll be working in a projective space. So the idea is you take the line and you say, we got positive infinity over there, and you got negative infinity over there, and we're gonna say, they're the same point. You go in this direction, you eventually wrap around, come back in the other direction, and you've wrapped up the number line into a circle. And then you can divide by 0. And a sort of another way of thinking about this, which is perhaps more intuitive than the stereographic projection, sort of another related construction, is to use literally the real projective line. So what is that? We can represent a location in a 2D plane, by fixing an x-axis and a y-axis. And, we can use those to have a coordinate system. We can represent a line in the plane, Descartes will tell you that it's y equals mx plus b, where, b is where the line intersects the y-axis, and m is the slope, right? Rise over run. Suppose the line goes through the origin, then the equation is just y equals mx. And so by choosing different values of the ratio, the rational number m, we can explore all of the lines through the origin. Well, except for one. What about a completely vertical line? Its run is 0. The equation is just x equals 0. But if our equation is y equals mx, then that would mean y is 0 as well. And that's not what we want. So what do? We have a divergent slope. The slope of a vertical line is infinity. And yet we know there's nothing weird about, okay, well, just all the possible orientations of a line. So, we solve the problem basically by, adding the vertical line, adding a point at infinity. And so then we can identify the rational numbers plus infinity as the lines through the origin in 2 dimensions. And you can kind of think about this. And there's like a subtlety here that, it's like you can treat the real projective line as a circle with opposite points identified, because obviously if it's lined through the origin, then, it doesn't, that intersects the circle at 2 places. And there's a kind of an interesting connection to this between, the idea that we can represent rational numbers like not in lowest terms. This is a classic thing, the notion of a projective space. We represent our line through the origin as like a little 2-dimensional vector. So if instead of writing a rational number like 2/3, we would write it like, 3/2. I just say that because rise over run. And, the idea will be, well, we'll get the same exact line if we multiply that by any number, because when we take the ratio between rise over run over the 2 components, any number that we multiply both of the components by will just cancel out. And, this should remind you of like what we talked about, the stereographic projection and the Riemann sphere and qubits, weeks ago, that eventually we're going to be working, not here, this is the real projective line, but coming up, we'll be working with the complex projective line. And, that's the theory of like spinners and stuff. And so that's why I bring it up here. But, this really, you can see the beginning of it here. And, whereas, infinity is kind of weird, and, we have to treat, the equation y equals mx plus b different from the equation x equals 0 as a little vector. The difference between a horizontal and a vertical line is just 0, 1 versus 1, 0. And so, and like before, when we were talking about our proof that 2 times 3 equals 3 times 2, if you run into an infinity, which is a vertical line, what's the problem? Why not just like turn your head sideways and turn that vertical line into a horizontal line, and then there's no more infinities. Okay, so that's that section. As you see, these sections get longer and longer. Any questions before I, continue sallying forth? No, I'm good. All right, well, so this is where stuff kind of gets particularly fun. Because, the story that we've just told is a fairly ancient one. I mean, obviously Pythagoras knew about, rational numbers, primes. But even then, there was known to be an anomaly, which was the irrational numbers. One of the myths is that one of Pythagoras' followers discovered that, the square root of 2 is irrational, and Pythagoras threw him overboard lest the secret get out. Because, if you go, the idea being, I guess, if you go around saying, the world's made of whole numbers, related by ratios, and then someone discovers that there's numbers that aren't ratios, you have a metaphysical problem. And we reach this because if we continue following our progression, we iterated counting to get addition, iterated addition to get multiplication. Well, you got to iterate multiplication to get what? Exponentiation. And exponentiation's inverse is to take a root. X squared, square root of x squared is x. If addition is, repeated counting all at once, and multiplication is repeated addition all at once, and exponentiation is repeated multiplication all at once. So 2 to the third, is 2 times 2 times 2 equals 8. 3 squared equals 3 times 3 equals 9, and so forth. And this comes up because, as Pythagoras tells us, if you have a triangle, a right triangle, the relationship between the base and the height and the hypotenuse is a squared plus b squared equals c squared. And if A and B are both of length 1, then the hypotenuse is the square root of 2.
This is what the follower of Pythagoras said in response to Pythagoras. Rationalists wearing square hats think in square rooms, looking at the floor, looking at the ceiling. They confine themselves to right-angled triangles. If they tried rhomboids, cones, waving lines, ellipses, as for example, the ellipse of the half moon, rationalists would wear sombreros.
That's great. Wait, where is that quote from?
It's Wallace Stevens.
Oh, nice. Yeah, I have to look that up. Thank you. So let's prove very quickly. I mean, if you've never seen it before, this is like a classic proof that the square root of 2 is irrational. And just like the proof that there's an infinitude of primes, it's a proof by contradiction. So, I don't know if this is exactly, how, the Pythagoreans thought about this, but certainly, I think it's the easiest way of seeing it. Well, actually, I'll show you an even easier way, but here's this. Okay, so suppose that the square root of 2 is some p over q, a rational number in lowest terms, which means that p and q share no factors in common. Okay, so we have square root of 2 equals p over q. Well, we can square both sides, and then we get 2 equals p squared over q squared. And then we can multiply both sides by q squared, and that gives us 2q squared equals p squared. Well, what's that saying? It's saying that p squared has a factor of 2 in it. And that actually means that p has a factor of 2, and p squared must have a factor of 4. Because if p squared has a factor of 2, and it's a squared number, it actually must be divisible by 4. The p must be divisible by at least 2. So we can factor out that 4 by introducing a new symbol. We say r squared equals p squared over 4, and rewrite our equation 2q squared equals 4r squared. Well, then we can divide out by 2. Q squared equals 2r squared. This says that q squared has a factor of 2, really a factor of 4, just as before with p. And so we've shown that both p and q are even numbers, but we assumed from the beginning that p and q had no factors in common. Therefore, we've reached a contradiction, and our initial assumption must have been wrong. The square root of 2 is not some p over q. Square root of 2 is not a rational number. It must be a new kind of number, an irrational number. And you can see that it has something to do with 2 dimensions. We can use a rational number to convert between units measured, a horizontal ruler and a vertical ruler. But we can't use a rational number to convert between either of those 2 rulers and a ruler at 45 degrees. There's no way to come to a common 1 between them. And actually, I think this is the simplest proof that something like the square root of 2 is irrational must be true. Think about how a triangle is like actually displayed on your computer screen. Your computer screen is a grid of tiny little pixels. And so, it's no problem to draw a straight, like a horizontal or a vertical line. But when you go to make a diagonal, you're going to have to zigzag. And therefore, technically, the length is going to be a little bit off because of this zigzagging you see here. It's all pixelated. Now, the idea is that if we keep adding finer and finer zigzags to our diagonal, we'll get ever closer to the hypotenuse's actual length, like the square root of 2. But that's an assumption that we can always refine our zigzags, which is sort of an assumption about continuity, that between any 2 points there's a third point. And the idea is well, if you imagine shrinking the grid space to 0, then the diagonal's length will be exactly the square root of 2. But I want to emphasize that in some ways, whether an actual length is irrational or not is somewhat in the eye of the beholder, in the sense that suppose we set the hypotenuse to be of length 1. Then using the Pythagorean theorem, we find that the base and the height, if they're the same, have to be 1 over the square root of 2. So if we, imagine that the base and the height are 1, then the hypotenuse has to be square root of 2. But if we imagine the hypotenuse is 1, then the base and the height have to be 1 over the square root of 2. So, you can't get rid of the irrationality, but you can kind of pick your poison. In this latter case, it's like imagining if instead of we started with horizontal grid lines and tried to make an image of a triangle and end up having to do zigzags along a diagonal. But what if we had our pixels arranged diagonally? Then the hypotenuse would be a nice little straight line, but the base and the height would have to be little zigzags. And we'll get the exact result, if we, again, imagine shrinking those grid lines to an infinitesimally small size. But that's the whole issue. What is this? What the heck are we talking about? Shrink the number down to shrink the grid space to infinitesimally small size. There's something going on here that's a little bit more subtle than what we encountered with the rational.
Matthew, if you just expand the pixels, you have to decide what you mean by the distance between the two pixels. And if you mean going up vertically and across horizontally, then the hypotenuse of legs 1 and 1 would be 2. So you have to mean something else by the length between the 2 points.
Right. I mean, I was just thinking about counting the number of, colored little squares, I guess. But you're right. Yeah. Because they have to be weighted by their size. So, how can we work with the square root of 2 if it's such an irrational number? I mean, obviously we can just treat it as a symbol to which we can apply algebra. Square root of 2. Maybe we never have to calculate it. We'll always square things in the end and get a 2. But if you want a value for it, you could approximate it. So, a very ancient method of approximating the square root of a number n is just to start with, just guessing a number. Call your guess G0. And then if you think about it, if G0 is an overestimate, then n over G0 will be an underestimate. Therefore, the average of the two should be a better approximation. So then your next guess is a half, the average of the two, a half plus the first guess plus n over the first guess. And then you make the same argument for that guess. If it's an overestimate, then n over G1 will be an underestimate, and that gives you your next guess. And so the longer we do this, the closer our guess will be to the square root of n. And we can say that the square root of n is the unique limit of this procedure. And so we can approximate the square root of n as closely as we like. And so, I have it worked out here. I think I took this part from Wikipedia, I have to say, but the square root of 2 is approximately 1.414213. And you see we get the series of fractions that get ever closer to it. Now, this is the first time you notice here where we've used decimal notation. And so let's just talk about that. Again, I'm sure this is, obviously this is stuff that many of us know. But, my point is to kind of if you want to talk about, how tricky quantum mechanics is, it's good to start from, our most elementary ideas about what numbers are. So, we have exponents around now that we're at this stage of the game. And so we can use a base n system of representation for our numbers, as we commonly do, right? 123 is just 1 times 100 plus 2 times 10 plus 3. So, now we sort of, although we talked about counting numbers before, we had sort of interpreted those as piles of pebbles, now we're sort of fixing the idea of numerals or digits, 10 digits, 10 fingers. So we have 0 through 9. And we can represent any number as an ordered sequence of those numerals with the understanding that they weight the powers of 10 or whatever the base is in the sum.
I ask a question about it's sort of historical, just out of curiosity. When the when irrational numbers were realized, why was the reaction to want to act like they don't exist versus to acknowledge that they exist, but maybe say like they represent sort of unpleasant things, maybe like aesthetically they're not pleasant, and so we can kind of maintain our pride in having having the rationals as our like center piece, but these other things are ugly, but they're there, versus like rejecting their existence entirely. Do you know historically what the?
Yeah, absolutely. I mean, again, it's a bit of a myth. We don't really know exactly, what went down. I think that, that particular myth that like they murdered this guy to keep, the word getting out about square root of 2, I mean, I think became particularly popular in, during the scientific revolution later on, because it was so analogous to like the Catholic Church fucking with Galileo or something. Like, it's this like idea, like we got these like smarty pantses out there and they're discovering things, but the powers that be are down.
Still had some basis, and like why wasn't the reaction just like how things are now, which is like, oh cool, look at that, that's new.
Yeah, I mean, certainly like the Greek mathematicians like took it to heart, like and tried to define their notion of magnitude in subtle ways, anticipating many of our modern ideas of like real numbers and like limit procedures. So in fact, a lot of like especially Hellenistic mathematicians like Euclid, took this idea like very seriously, like, and we're not trying to put it, throw it, keep it under the rug or anything. I don't know. I mean, there's a lot one can say about it. Like, for example, you talk about like, is it aesthetically pleasing or not? So, if you think about the musical ratio of like the square root of 2, like what happens if you take a frequency and multiply it by the square root of 2 and play the 2 notes together? What interval is that? And it turns out it's the interval basically from C to F sharp, which is the tritone. And it's actually like the most dissonant interval. And in the Middle Ages, famously they called it the devil in music. And so maybe that had something to do with it. I don't know.
Can I say something?
Yeah.
Negative numbers were considered the work of the devil also. And this is written down. There's no mythology here. This I wish we were fairly rid of them, someone wrote.
Yeah, I mean, I think there's a better case for getting rid of negative numbers, since after all, there's like political implications to that, right? It's debt forgiveness.
The wiki method that you use to begin to approach the square root of 2 lessens the sting, because you near the possibility of the psychotic break
Yeah.
with the rational number very slowly, and so it takes away the sting.
Well, soon enough we'll talk about uncomputable numbers, which are truly psychotic.
And also, when was pi known about, and when was it realized that it was irrational?
When was the square root of 2 realized to be irrational?
No. Saying all this going on with, I don't remember offhand, or if I ever knew, like when pi was. Sorry, I'm sitting back. When pi was known about, because certainly there have been circles for a long time, and when it was appreciated that there's pi in there, and then further on that it's an irrational number, so you kind of can't. Another situation where you might not be able to escape the inevitable.
Yeah, great question. Yeah, I'm not sure about pi. As far as the, I'm just trying to think. I mean, certainly, irrationals are discussed in Euclid. I mean, who was like 3rd century BC maybe, and Plato's a couple hundred years before that, and he knows about it.
Is it?
You
Is
know,
it?
you can find like Babylonian and like Egyptian mathematical writing where they will like give you approximation algorithms for like stuff like that, which like suggests that they like knew like in practice that these numbers like couldn't just be like written down as like a rational number, you know? But you know, I would say that, yeah, like probably, you know, who first really started like meditating on this stuff is probably lost to the mists of time. But by, you know, but certainly like people were talking about this stuff like in the Mediterranean, at least by 500 BC. I mean,
The Egyptians used an approximation 22/7 for the design of the pyramids, and the Indians were using astronomical calculations to near the pi, as a, you know, in the same way that you were doing with your wiki method.
And in the case of the pyramids, do you know how pi was, you know, involved? Was it like geographically where to locate because of the curvature of Earth, or like, you know, the pyramids?
oh, that would have, yeah, maybe. I don't know. I don't know if we know about that. The pyramids are pretty old. It's a great question, though. I mean, certainly, I mean, they're aligned with the stars. Yeah, whether they were thinking about the curvature of the Earth, you know, I don't know.
Yeah, just with the shape of the pyramids, I don't see a, you know.
Yeah.
There was just a tablet found at one of the sites, one of the mining sites of the stone, which actually explains some of the principles, some of the design principles. That this was very recent, Nick.
Oh, very cool.
Is there?
I'm sorry.
Yeah.
No, can I add something?
That tablet?
Pi is only irrational in our numbering system. Pi is an exact number, you know, and it's completely rational in terms of measurement. So the problem is with our way of numbering things.
Well, that's sort of like what I was saying about the square root of 2. Like if you have the base and the height both be 1, then the hypotenuse is the square root of 2. But you know, if you have the hypotenuse be 1 and the base and the height, so you can shift around like which number you're going to have to treat as irrational, like given your number system, but like you can't get rid of it entirely. I mean,
Unless you
mean like, you know, the value of pi is sort of depends on like the curvature of the space that you're in, you know, so like.
No, but the point
is exactly 3 if you're in a funky curved space.
The point is we can invent a new measurement system, and in measurement, pi is exactly the circumference divided by the diameter.
Yeah, but then the circumference.
Right, but like, how do you measure a circumference? Like, you know what I'm saying? Like,
but you see,
you'd need like a circular grid system, right? If you wanted the circumference.
No, you can have a circle and just stretch it out to a straight line. You can cut the circle and stretch it out.
Well, but the thing is like, you know, to follow the analogy from before, it would be like you could have the circumference be like a rational number if you're working in like circular coordinates, and then like each part in the circle would be like a little curved segment, but then the diameter would be irrational. It would be like made up of a bunch of little curved segments trying to approximate a line.
You're defining all these things in terms of our construction of what math is. And
I don't deny that.
This is not the way nature constructs it.
I think maybe a more practical way to be critical is in terms of precision. Sure. You know, you also can't be infinitely precise with just the number 1. You don't know that somewhere way out there isn't like a deviation from a 0. You know, and so you have precision of pi up to some amount, and that's sufficient for whatever your purpose is.
Nature deals only in precise quantities. It is we, because of our incomplete mathematics, that have to use approximations, or in this case, irrationals. Nature deals in exactitudes. The circumference of a circle relative to its diameter is an exact number.
Right, but so like, right, like
where is there a perfect circle in nature?
Yeah, well, that's another good
Oh,
point.
yeah, well, that's another issue, that we idealize all these things anyway. These are all
Well,
idealizations.
we're trying to find an
No,
average.
there's no absolute certitude. The distance between 2 points in nature cannot be determined with a higher precision than Planck length. There's a limit to the precision of a distance. Planck length, that's it.
And you better do the calculation within the Planck time.
Least by 7.
Because if not, Moshe, we're not going to accept it.
No problem, it's done already. I did it in half a Planck time.
Multiple times.
Can I just defend those those superstitious people in the Middle Ages who thought that negative numbers were the devil's handicraft?
Yeah.
Because once you get into finance and you start thinking about compounding returns, if you see that you make money on, you put in a positive amount of money and make money, and then you put in a negative amount of money and lose money, you could actually lose more than you made, but when you compound them, you get a return that's positive. So this is the kind of thinking that led to saying things like the negative numbers are the devil's handicraft.
Well, I want to prove that negative numbers are the devil's handicraft by saying that that the banks take $1, okay, in a deposit, and then they loan $8, $9, or $10, give you at the present moment 0.07% in interest, and then charge you 18% on your credit card. So that is the proof that negative numbers are the devil.
Now, Vic, you're talking about reserve requirements, the reserve ratio, and it's not the banks who create the money, really. It's the Federal Reserve. No, you're the banks with the authorization of the Federal Reserve. So maybe they're the devil. Get Jerome Powell on the line.
Yeah.
The devil.
Yeah, I mean, like all this, in all seriousness, like this brings up like I think the important point that, numbers cannot be separated from things like politics, from finance, from like how they're actually used. And a lot of the reason why numbers are so fraught, like in our culture, is precisely because of this. Like I was saying, to number things is to treat them as indistinguishable, which does potentially kind of like violence, to the unique identity of like the things that you're numbering. And so, it's absolutely true that it's always good to be suspicious of like, the tax man showing up to number. I mean, there's an interesting book called like Seeing Like a State, where he talks about how, the development of agriculture in like the early modern period was mainly, and even before that, like the reason that, wheat-based civilization caught on was because it was very easy to tax. It's very easy to just be like, all right, I got this much in the field and we got this many bushels of whatever. So that, whenever someone from the state comes to start numbering things, people have, I think, with good reason to be suspicious. And so numbers are never just numbers,
The first number system amongst the Sumerians was an attempt to count bushels of grain.
Yeah.
The first writing system of numerical writing system was an attempt to count bushels of grain.
I've heard, and this may be contested, but I thought it was very interesting that, the Sumerians, they found these stores of like these little clay balls. And when they open them up, they're full of these little, tiny little spheres and like tiny little pyramids and like little cubes and like different tokens. And the idea was like kind of at the time that, there were lots of different token systems, not just one kind of money. And like when people would make some kind of deal, like the way the contract would be kind of signed and affirmed and fixed, quote unquote, in stone, was to, suppose you're trading like, X of these for Y of those, you put X pyramids and Y cylinders together, and then you wrap them in a clay ball and fire it. So then you can't change the number that's in the ball. And you can see, if like someone's messed with it and tried to change the terms of the agreement, like if someone's like cracked open this clay ball, and in order to remember like what was in them, they would make marks on the surface of the clay ball in the shape of like a little pyramid or a little cylinder or whatever. And those eventually became the origins of the Sumerian cuneiform.
But then how can you tell if the pyramids and cylinders are dead or alive?
That for the philosophers.
Yeah, but what about counterfeiting, Algie?
It is very simple. They are dead and alive. We know this.
Speaking of stuff like this, did you guys know that Isaac Newton was in charge of the mint?
Yeah.
They put him in charge, and he was a brutal motherfucker. I mean, like, if you were caught counterfeiting
That was an upsetting.
early modern England, like, you would be killed
Yeah.
by Isaac Newton. Like, I'm not even joking. It's terrible. I mean, he may have been suffering from advanced mercury poisoning at that point. I don't know if that gives him an excuse.
I think he's also responsible for, am I on mute? No, for inventing the idea of putting the ridges on the dime and the quarter on their circumference, because doing that is difficult, and people were like shaving off when it was like silver.
Right.
It made it. That was his idea for handling that. But yeah, did you get that from? There's some like book of letters that I saw a guy give a talk on. I didn't actually read the book, but where there are a lot of correspondences to Newton.
Right, it was from a letter. Yeah, it totally was. I read it a couple of years ago, but yeah, it was from a letter.
Some people had written him like for asking for clemency, like
exactly.
I only stole like a sandwich, and Newton's like, sorry, buddy. He seemed to be kind of a dick.
Yeah, it's like we gotta preserve the health of the money supply. Like, apparently more important than human lives. Well, anyway, so we were talking about the base number system. We all know about that. It's interesting, you get numbers like a third, have these repeating decimal expansions. Okay, and the irrational numbers, as you may know, have infinitely long decimal expansions that don't repeat. And so, you either have to calculate them all, which is impossible, or give some rule that, you could maybe prove that if you keep following this rule, you get ever closer to this irrational number. And so clearly at this stage, in a deep way that is different from before, when we're just talking about rational numbers, infinity is playing an important role. Not like the perspectival infinity of, like wrapping up the line into the sphere, the line into the circle, but the infinity of like imagining like doing something, repeating some procedure over and over and over again. And, I thought I would mention at this point, that there's different kinds of infinities, as you probably know. There's the infinity of the counting numbers, 1, 2, 3, 4, 5. But now we're dealing with, this perhaps, one way to think about it is the continuous infinity of the line. Between any 2 points, there's a third point. The infinity of the real numbers. And this infinity is actually larger. So this is,
Between any 2 points, there are an infinite number of points.
Sorry?
Between any 2 points, there are an infinite number of points.
Oh, well, sure. Yes.
Yeah, more than
that's the implication of that. Yeah, definitely.
Tell that to Planck.
Tell that to Planck. Right. Yeah, totally. It's like, we're starting, but with what we can imagine in a way, and then we'll see how physics layers stuff on top of that. So yeah, there's a famous, very nice proof, the diagonal argument from Cantor. that shows there's more counting numbers than real numbers. And in fact, one prerequisite is just to know that there are no.
No, you mean to say more real numbers than counting numbers.
Yes, sorry, whatever I said, yeah, my bad. So one thing you first should note is that there are the same number of rationals as counting numbers. So they can be, what we mean by to count in this case is to put into a one-to-one correspondence. So we're gonna give a rule that like pairs elements uniquely. And that's like a rule for enumerating. And I'm not gonna go into the proof of like the exact proof of like why there's like as many rational numbers as counting numbers, but you can see that there's a sort of obvious enumeration of the rationals where you have like 1 over 1, 1 over 2, 2 over 1, 1 over 3, 3 over 2, 2 over 3, 3 over 1, 1 over 4, 4 over 3, 3 over 5, 5 over 2, 4 over 1. You could sort of imagine that. Okay.
But it's only because we're defining, right? It's the definition of a rational number. We're defining rational numbers as countable. So obviously there's a one-to-one correspondence.
Okay, yeah, I mean,
between the countable numbers and the rationals. That's our definition.
Well, I mean, in some ways it makes sense, but in other sense, I mean, obviously, I mean, there's a lot of rational numbers between 0 and 1. Is that really obvious that it's this, same infinity as that you get to by just being 1, 2, 3, 4?
But they're all countable. The digits are countable.
The digits are countable. Right. Yeah. Okay. Sure. Yeah. I see what you're saying. Yeah.
Definition of countable. Yeah.
Okay. So here's a sort of quick version of the diagonal proof of Cantor. So suppose we're working in base 2, and our numbers are binary digits, and we try to make a list of all the numbers by just enumerating over the counting numbers, and we're putting them in some order. Order doesn't matter. It seems like we can get all possible sequences of zeros and ones just by counting, 0, 1, 1, 0, 1, 1, 1, 0, 0. And you can imagine if you want to, in a square grid, padding, these numbers, zeros to the left. So we imagine making a list of all the numbers that we think we can count. And they're each a sequence of ones and zeros. So we have this infinite grid. And then, you see the recurring theme here is the diagonal line, Cantor imagines going along the diagonal of this matrix and flipping every 0 to a 1 and every 1 to a 0. And what do you get? If you imagine a sequence of ones and zeros along the diagonal, by construction, that sequence will be different from the first sequence in your list in the first place, different from the second sequence, second one in the list in the second place, different from the third row in the third place, and on forever. Therefore, even though this sequence is completely well-defined, we're like, oh, we'll just enumerate all the ones and zeros, put them in a list, and then go along the diagonal. It's a perfectly definite procedure. And yet we've been able to generate a sequence of ones and zeros that by definition can't be on that list. And you can think about such a sequence representing an irrational number. You can get different ones, for every possible ordering of the counting numbers. And this is a proof that, there are infinities greater than the infinity of the counting numbers. There's some subtlety involving, the continuum hypothesis, which we won't talk about here. But you can iterate this argument to show that, there is an infinite hierarchy of ever more infinite infinities. So there's not just one kind of infinity. On that same point, thinking about 19th century, thinking about, real numbers, there's the famous definition of a real number involving the Dedekind cut, where we imagine the rational number line and cutting it into 2 infinite sets, A and B, such that every element of A is less than every element of B, and that A has no greatest element. We then consider the least element of B, Well, if that number is rational, then the cut defines that rational number. But there might be an irrational number that's greater than every element in A. Since A has no greatest element, then really the first number in B ought to be an irrational number, but instead there's a gap since we're just working with rational numbers. And so we fill in that gap, and that's the irrational number defined by the cut. A then contains every rational number less than the cut, and B contains every rational number greater than or equal to the cut. So clearly at this stage, infinity is playing a very crucial role, and also kind of self-referential logic, approximations where we feed the outputs back into the inputs, lists which we make and then negate to infinity. And the culmination of all these ideas can be expressed in terms of computability, the general theory of following definite rules. After all, there's many ways to calculate things, feeding outputs back into inputs and so forth. Not all of them correspond to rationals or even real numbers. And now here's a fun thing. Maybe you've heard of this, maybe you haven't. We can build a computer out of fractions. And this is a construction due to John Conway, rest in peace. And it goes by the name of Fractran. And this is like one of my favorite things, I have to say. Okay. So a computer program in Fractran is an ordered list of fractions. So for example, here's the source code, 17/91, 78/85, etc. The input to the program is some integer, call it n0. The idea is that you start going through your list and you try multiplying n by the first element in the list. If the denominator cancels out and you get an integer back, then that's the output. You stop, go back to the beginning and start over, and that's like the new input to the program. But if you don't get an integer back, then you move on to the next fraction. Try multiplying it. If you get an integer back, oh, that's the output, go back to the beginning. If not, go on to the next fraction. Multiply it. Do you get an integer back? If so, oh, stop, feed it back in. If not, move on to the next fraction. And if you get to the end of the list without getting an integer back, then the program halts. And that's Fractran. And it's complete for universal computation. Any computer program you write on any computer, any classical computer, can be rewritten as a program in Fractran. So
when did he come up with this? I'm curious because he called it Fractran, not fractal. I guess fractal, the word fractal had already been used.
Well, I guess it's a play on Fortran. He invented it in the 70s.
But this probably, fractals probably, Mandelbrot fractals probably predate this.
Maybe, I don't know. I mean, fractals, I feel like fractals were kind of, maybe I'm completely wrong about this. I feel like they were popularized in the 80s, but Mandelbrot had been working on them since at least the 50s.
Oh, yeah.
But yeah, I think Conway came up with this in the 70s.
I worked in the same place as Mandelbrot. I know him. He was working on this maybe as early as the 40s.
Wow.
He was practically retired by the 80s. We both worked at the IBM Research Lab together.
Oh, cool.
Yeah.
Yeah, there's some great videos on YouTube of him talking.
Because Fractran seems like an odd term.
What is the advantage of this rather intricate system of programming? Well,
yes. In fact, you can find it on lists of so-called esoteric programming languages, which are designed to make your brain hurt. But I bring it up because I want to
hide the code, to hide the actual source of the code. Yeah. Is that the purpose?
Well, I think that I'm interested in it for two reasons. One is that it allows us, in like my little scheme here, to define, it's like one way of defining what we mean by a real number, in terms of like a list of fractions representing the computer program which approximates that real number. But also, it has a deep relationship to Gödel's incompleteness theorem. Because if you recall, and I'm going to go into this in like a paragraph or two, but if you know anything about that proof, you know that Gödel used this thing called the Gödel encoding, where he uses like the prime factorization of integers to encode statements of mathematical logic as integers. And the construction is kind of very like Fractran. So, you know, and I just think it's interesting because like, it's so, although it's weird, I mean, it's so simple at the same time, you know. So for example, this program right here that I've listed out, I mean, I didn't come up with it. I think Conway himself did. This is a program which generates the prime numbers. So if you start this program with the input 2, it'll generate a sequence of integers that, like, in progression in the sequence, like there's other numbers in between, but it'll generate the powers of 2, 2 squared, 2 to the 3rd, 2 to the 5th, 2 to the 7th, 2 to the 11th, so 2 to the prime numbers. One of the simplest Fractran programs is just 3 over 2, and it adds. So if you give it an input, 2 to the A times 3 to the B, it eventually outputs 3 to the A plus B. And you can come up with, you know, there's programs, you know, for subtraction, for division, you know, whatever. And here's like why it works, right? So, you know, just as we can write out like an integer in the base n representation as an ordered list of numerals, we also know we can write out an integer as a product of primes. So 60 is 2 squared times 3 to the 1 times 5 to the 1. Now, although the primes are unordered in this product, the primes themselves are ordered. So that we could like denote 60 as like 211, whereas understood that the first digit is the exponent of the first prime, the second digit is the exponent of the second prime, and so on. So to have a computer, you need a memory, a set of registers. So our computer uses an integer as its memory, and each prime in the integer acts as a register. The value in that register is the exponent of that prime. Multiplying by fractions allows us to shift data between the registers, and the rules turn out to be complete for universal classical computation.
Could you use this program that generates primes to create, at this moment, given that it's 6:15, a virtual Thai dinner that I could have while I remain here listening?
Well, it brings up the point. I'd love to. So I wonder if someone's written like a source code translator. You know, if I write a program in Python, could someone just print out, you know, a list of fractions for me? You know, in Gödel's proof, what he does is he sort of is like, well, I can assign to each symbol in my formal system like a number, and then encode a mathematical formula by saying that if I want the symbol in the first place in the formula, it's a power of 2. So I stick like the number that symbolizes my mathematical symbol as the exponent of 2. And then the exponent of 3 is going to be the symbol in the second place. The exponent of 5 is going to be the symbol in the third place, and so on. And so no doubt Conway was thinking about Gödel's famous proof when he came up with Fractran.
So again, my question, Matthew, is there any way to reverse this and break the RSA security system? You know, starting with a number and working back to get the primes. That should be an interesting project for one of us.
Yeah, I mean, you know, I don't know. It's like the world seems to be suggesting things like, you know, whatever, P doesn't equal NP, you know, to put it in like the terms of computational complexity. Like there's this like sort of asymmetry that is very pervasive, right? It's like, it's easy to take a derivative, like it's hard to take an integral. It's easy to multiply a bunch of numbers, hard to break them back down again. Like it's might be easy to check a proof, but hard to come up with a proof. There might be some conceptual revolution where it turns out, those two things are easy, actually, as easy as each other. But I suspect not. And it's a matter of like representation, right? It's just like, if you represent a number as like, 124, then, it's easy to like notice, for example, that 123 is greater than 122 and less than 125. Like that representation of a number like makes it easy to see like where the number falls in the order. But if I give you the number as like 2 times 3 times whatever, it's very difficult to know where that number is. But of course, you know quite well what prime numbers it's broken down into. So it's like multiplicative properties. So, there's like a trade-off. It's like one representation immediately at a glance, you're like, yeah, this is where that number is, its magnitude, but its decomposition is sort of, hard to know. But on the other hand, maybe you represent in a way, its decomposition's obvious, but then it's hard to tell what its magnitude is. So it just seems like, depending on what representation you're working with, like not everything is going to be equally conspicuous. And,
of course,
translating between the different points of view.
Quantum computing will make all of this moot because it will do everything so rapidly that all of our security systems will be for naught.
Well, that's true, except for the fact that you could use the quantum computers to create perfect, unbreakable encryption. So even as they utterly lay waste to all classical cryptographic systems, or so we think, at the same time, you can have perfect encryption with.
Can you? Wouldn't they be able to break their own encryption?
No,
like, the simplest.
you will violate the laws of quantum mechanics.
By doing what, Moshe?
By making copies of states of an electron or a photon, the no cloning theorem will prevent you from breaking the system. Basically, I send you an electron or a photon with a certain spin. If someone in between, an interloper, reads the spin of this particle in one direction, and you are going to read it in some other direction, they cannot possibly know in what direction you are going to read it.
So that would preclude a quantum computer from breaking a quantum code?
This will prevent an interloper from capturing messages.
Oh yeah, but not breaking the code. The code could be broken.
Yeah, but you can't do it without being noticed.
Well, yeah, I mean, right. Well, okay. Yeah.
Yeah, it's interesting. It's like it separates out that idea of like being noticed that you're meddling versus just like being able to crack the code, which classically, like you can crack a code without anyone noticing that you're doing it. But
yeah.
Basically, if I send you a message, you may know which bits have been corrupted or read by an intruder and which bits have not been read by an intruder. The bits, it's a message. And no one has ever read this message.
yeah, but the quantum takes it, it giveth with the other hand. It's
yeah.
Oh, it's so biblical.
Yes.
Well, couldn't you also like kind of try to, if you always have a system that's like servers that are always trying to crack everyone's codes, so everyone's message, they're always seeing that they've all been listened to. They're like, this is just
totally. Just fuck with everybody at once.
This isn't gonna work either.
The code breaker may not care if you find him out, as long as he broke the code and stole all your money before you could do anything.
Presumably, the recipient would have encoded in their decryptor, something that prevents the communication from continuing if detected, something like that.
Yeah, if you pollute the information environment sufficiently, then it's going to be hard to do anything. And that's the Donald Trump principle.
Who? Who's that? Is he still around?
Yeah.
I remember him from the 90s. I didn't know that he was still
Actually, it's like sounds like you could do a denial of service. Really trivial.
more like a denial of reality.
Anyway.
Okay, maybe I'll be able to get through this this section here, and then maybe we'll call it a night. And then that'll be kind of nice because the next time we can pick up with some more specifically quantum stuff relating to spin, as you'll see. But just to continue, where we're at, it was sort of leading up to it. Here's like a little way of thinking about the Gödel incompleteness theorem, or it's sort of related to Turing's halting problem. So here's a sort of simple proof of it. The whole thing rests on self-reference, right? Which these days we're all familiar with. Like everything on a computer is ones and zeros. The program is ones and zeros. The data is ones and zeros. It's all kind of flat. The instructions of the computer program, computing some numbers, can also be regarded as numbers themselves. And so naturally we can write computer programs whose input is other computer programs. And this becomes the basis of Turing's halting problem. And it's yet another example, both of a proof by contradiction and also a diagonal argument. So, it would be great to have a program, call it H, that takes as input another program A and an input I, and it tells you whether A will halt or run forever on the input I. In some cases, like that'll be like really obvious, like if A has just like an infinite loop, like right there, like while 1 equals 1, or if the program's just return 5, those are the obvious cases. But is there a program that can handle all the cases? So suppose there was, you run H on A and I, it returns true if A halts and false if A doesn't. And then you consider the Gödel function, or the Gödel program, G. And it takes a program A and an input I. And if A halts, then G runs forever, just in a loop or something. And if A doesn't halt, then G halts. And this is like exactly akin to going along the diagonal in Cantor's proof and just flipping all the bits. So then you consider H run on G with input G. This is supposed to return true if G halts on G, but false if G runs forever on G. But according to G, if G halts, then G runs forever. But if G runs forever, then G halts. Oh my God, my brain hurts. This is a contradiction. And so there's no program H that takes as input any arbitrary computer program and a starting input and can determine whether that program definitely halts or not on that starting input. The moral of the story being that if you want to know if a computer program halts or not, in general, you have to run it potentially forever and just wait and see if it actually does halt. There may be no shortcut. Now, like I'm not saying there never is a shortcut, but in general, there is no shortcut. And furthermore, there is like an intrinsic limit to computation. There are some questions which are in principle like not computable given like a scheme. And this leads to the more standard formulation of Gödel's incompleteness theorems. So, he proves it not, he proved these things in like the early 30s. Turing did his work about a decade later and knew about it. And Gödel's working in the framework not of computation, but of mathematical logic. So he assumes, the axioms that give you the elementary operations of addition, multiplication, subtraction, division, and some quantifiers like there exists and for all, not being too specific about the technicalities here. He then sets up a way of encoding statements of mathematical logic into numbers using, as I said, an encoding based on the primes. And in this way, statements of mathematical logic could then, talk about other statements. He then constructed a self-referential statement that led to a contradiction. Okay, so the full statement of the Gödel's incompleteness theorems are: a system of logic powerful enough to contain basic arithmetic is necessarily incomplete, and that there are statements that can be neither proved nor disproved by those rules of logic. One such statement, in fact, is the consistency of that formal system. In other words, whether those rules of logic lead to a contradiction. So that a system of logic powerful enough to contain arithmetic cannot prove its own consistency. It may, in fact, be consistent, but that can only be proven using a different system of logic. So like you could repair your like incomplete or insufficient system of axioms and rules of inference by adding yet more axioms and rules of inference, and then you might be able to resolve some previously unanswerable questions.
That's easy. That's easy. If you cannot prove that it is consistent and you cannot prove that it is inconsistent, then if you add one more axiom, the axiom says it is consistent, then you have a consistent system, because this new axiom, by definition, will not contradict anything that you have already.
Absolutely, yeah.
It says it's consistent, so you're home free.
Yeah, I mean, like the crucial thing there is, like you have to add that axiom, which it's, like at the turn of the 20th century, there was this sort of dream, which was that mathematics could be reduced down to a mechanical procedure, right? Like, so if we just figured out, like, there'd be just, all right, there's these 7 axioms for all mathematics. We plug them into a computer, we like turn the crank, and it finds like all possible combinations of those symbols, given those rules of inference, then that little machine would like eventually output all the possible like truths, all the possible theorems. And what this proof shows is that that can't be the case. That because you have to start with a certain set of axioms, and they're going to be necessarily limited. And if you want to resolve certain questions, you may have to add more axioms. And so the process kind of has to unfold. You can't just start from one single set.
Not to get too philosophical, because this is supposed to be science, but didn't Karl Popper say that, it's got to be falsifiable? If you can't falsify it, then what have you proven? You have to start with some unproven set of axioms, because the basis of our mathematics is not falsifiable under Karl Popper's rules.
Well, I mean, it's falsifiable whether those axioms like lead to the conclusions you think they do. But yeah, I mean, exactly. You have to assume some stuff to get off the ground.
I do not agree with what you said, Michael. There's no reason why our set of axioms is non-falsifiable. In principle, you could find a contradiction within our set of axioms. For instance, one such contradiction was found by Russell, the Russell paradox. He found this contradiction within the set of axioms that we took as the right set of axioms of mathematics. He found the Russell paradox, and the axioms had to be changed to take care of the Russell paradox. So it has been falsified and corrected.
Has all of our mathematics been falsified?
No, it is falsifiable. It is falsifiable. It is not, what we have right now has never been falsified.
Right.
So we continue to use what we are using right now. But,
right.
But it definitely is falsifiable.
Well, maybe certain aspects, but not the entire basis.
I'm finding an example.
Entire basis.
That's Russell showed that?
Yeah, the Russell paradox. It is very similar to some of the stuff that Matthew just mentioned before.
Yeah, I mean, so Gödel, like himself.
Catalog of catalogs that don't mention themselves.
Yeah, like, so, the story goes that, after, so like Cantor was coming up with, the diagonal argument and everything at the end of the 19th century, and, made set theory a popular thing among mathematicians. And it was in that context that Russell formulated his paradox about, self-reflexive set membership. And then he and Alfred North Whitehead spent a whole bunch of years trying to write their Principia Mathematica, where they were going to sort of quarantine, these different self-referential statements into one, kind of hierarchical system of statements that only these can relate to these statements, and build up all of math from an axiomatic system, which would have this feature that like a computer, like a mechanical device would just, you plug it in these rules of inference and these symbols, and it would just generate all the theorems. And it was, out of that world that, Gödel came and eventually showed that such a project was, in some sense, destined for failure. Of course, it's like in practice, it's just assume some more axioms. In practice, it's not a big deal. But, it gets at the point I was making way back at the beginning, can we reduce our concepts to one set of universal basic concepts? And, Gödel's result seems to suggest no, that there's no one set of master concepts that can be used to understand everything.
Before we start to build a computer that can do it, imagine that it is possible to build this kind of computer. This is definitely going to be a quantum computer with gazillions of qubits in it. It is going to cost billions and billions of dollars. Suppose you spend all this money, the computer runs, and after it runs for a while, maybe even a long amount of time, it discovers that the set of axioms that it uses is inconsistent. It discovered that it itself is inconsistent and therefore nonsense. If it
if it discovers that, it's wrong.
It destroys
right?
itself.
It's hard to trust that result at that point.
Yeah.
But this computer will destroy itself, and our investment of billions of dollars will disappear.
More
Something will fail sooner than
it would prove that quantum mechanics is false.
It will prove that we do not exist.
Well, it is.
Who said that? Actually, you're right. It's only one a very approximate explanation. You're absolutely right, Victor.
I have another musical interlude for you guys. So yet another thing that's sort of related to Fractran is
Getting closer and closer to the point where one has to choose between, feeding oneself on the food of physics or thriving on the physics of food. And I'm beginning to near very, very slowly, like you neared the pi and like you neared the square root of 2, the need for the physics of food.
No,
okay, sorry.
Nothing to stop you from eating while you continue to enjoy this wonderful discussion.
Yeah.
Voila.
Look at there he goes. There he goes. There he goes.
Can be done.
For an ample fee, we deliver.
So there's a famous open conjecture called the Collatz conjecture. There was some recent work done on it, actually, by Terry Tao. I don't really recall the details of it, but it's still unresolved, so maybe you guys can figure it out. And actually, you can think about it as a special case of a Fractran program. So here's the idea. Here's like the simplest version. You start with the counting number n, and the goal is to get to 1. If n is even, you can divide by 2's until there's no more 2's, and then you're left with an odd number. Well, you could add 1 to it, and then you get an even number, and then continue to take out 2's until you can't. And then you add 1. And obviously, that will get you to 1 in the end. But there's a related question you could ask. You could be like, well, what happens if, okay, if n's even, you take out 2's, but when it's odd, what if you multiply by 3 and then add 1? You'll get an even number. Take out 2's till you're left with an odd number. And then multiply by 3, add 1, divide out by 2's. Will you always end up at 1? Collat's conjectured yes, and no one knows for sure. You can imagine the number as a string of bits. Taking out 2's is just popping off 0's, shrinking the string. Multiplying by 3 and adding 1 stretches the string. Will the shrinking and overcome the stretching? Another the metaphor for it is often known as the hailstone problem. The idea being that the number is like a hailstone falling to earth, due to gravity, but it's being buffeted upwards by the wind. Will it stay up there forever, or will it eventually, where all the hailstones fall to earth? And the problem may very well be undecidable. We don't know. But you could see that it could be, because if you sort of like interpret this as something akin to a Fractran program, you can see that like the dynamics of this thing could be, somewhat arbitrarily complicated. You can also consider generalizations of it. Why not take out 2's and 3's if you can, and then multiply by 5 and add 1, or take out 2's, 3's, 5's and multiply by 7 and add 1. So here's the basis of a little musical piece involving a kind of mathematical 4-part harmony. So I take these 4 rules, the n+1 rule, the 3n+1 rule, the 5n+1 rule, and the 7n+1 rule. I imagine starting with the number n, evaluating each of the 4 rules in parallel until they all hit 1. Now they're going to hit 1 potentially at different times. So if 1 hits 1, it's going to start going into a repeating sequence. So in the 3n+1 rule, if you hit 1, it'll go up to 4 and then 2 and then 1, and then 4 and then 2 and then 1. And so if one of these sequences ends, then it just sort of bounces there until all the other 4 have ended. And then we move on to the next number. And what we're going to do is we're going to hear it in exactly the same way we've been hearing things. So each number, as it comes up, we're going to break down into prime numbers, create a chord, hear it, a bunch of sine waves, and this is going to be a musical piece, which I will now play for you. Like, hear these like sort of wandering around, and then it'll like reset, and then you'll hear the next number, and then the next number, and then the next number, and then another number, and then another number. So you're hearing the n+1, 3n+1, 5n+1, 7n+1 rules being evaluated in parallel, forming a 4-part harmony. So this goes on for 4.5 hours, and it reached 1 every time in all 4 cases. So we don't know. But I specifically chose those 4 rules because they, involve the simplest prime numbers. So wait, let me turn down the volume on this. Oh wait, this is a nice one. Look at this. This one's taking forever to return home.
This is what would happen if Arvo Pärt suddenly became a Milton Babbitt fan.
Give me all your stuff. The one reason I like this is for exactly the reason that we were talking before about like tuning and stuff. So we were talking about Pythagorean tuning before. And to some extent, you know, Pythagoras gets credit for this idea of the circle of fifths. So if I start, you know, you can see it right here. If I start with D and I go up a fifth, I get the note G. I go up a fifth again, I get C, and then F, and then B flat, and then E flat, then A flat, then D flat, G flat, B, E, A, and back to D. But if you think about it, that's impossible, because going up a fifth is like multiplying by 3, but going up an octave from C to C or D to D is like multiplying by 2s. So how can a power of 3 ever equal a power of 2? It's not going to happen. It just happens that the circle of fifths works because sometimes you multiply a bunch of 3s together, they end up being really close to a power of 2. In fact, so close that the human ear cannot distinguish the difference. But of course, there is a difference. And so, you know, that's why we use the, we don't generally use the Pythagorean or tuning or just temperament. We use the even temperament, so that, you know, the ratio of adjacent notes, like I was saying before, is the square root of the 12th root of 2. So that, you know, you go up 12 notes and then you get exactly an octave. But I like to think that the 3n+1 problem kind of like puts a new twist on this old issue of Pythagoras' circle of fifths, right? You know, Pythagoras is, you know, his stories are all about these dramas, right? These dissonant dramas. Like, I love rational numbers, but then I discovered the square root of 2. Like, I discovered that, you know, the note in the scale is a perfect circle, except the circle doesn't really complete. So in some ways, yeah, I'll say that the theme of this section is, you know, incompleteness. So what I like about the 3n+1 problem is that it's sort of like saying that the next best thing to the circle of fifths might be true, right? Because going up by fifths is like multiplying by 3, maybe like dividing out some 2s, and going up an octave is just going by 2s. But what if instead of going up by a fifth, multiplying by 3 over 2, instead we go up by 3, add 1, and then take out 2s. Go up by 3, add 1, take out 2s. Like, go up a fifth, and then a little bit more. Okay, now try going back down. You know, go up a fifth, and then 1 more, and then da-da-da-da-da. Which in some ways is like the next simplest thing you could imagine doing, besides just going up by fifths. So that if the conjecture were to be resolved as true, then it would mean that just a +1 solves Pythagoras' musical crisis. And the next best thing to the circle of fifths can close. Another little music thing is, instead of the 4-part harmony stuff, it's like, we'll start with the 3n+1 rule, and we're just gonna count rapidly, like 1, 2, 3, 4, 5, 6, 7, da, da, da. And each number is just gonna spawn off a collat sequence. And we're gonna hear each number in that sequence broken down into a chord. And they're just all gonna be like on top of each other. And we're gonna really hear it, and it's gonna really sound like a hailstorm. And you're gonna be able to hear the numbers like whizzing down, because what is going down by 2s sound like? It sounds like, you know, going down like by octaves. So the numbers will get pushed up, and then you'll hear every once in a while one of them like whizzing down. And it's a little crazy, but here you go. Okay. These files are online. I'm sure it sounds sort of particularly hard to hear on the Zoom or whatever. But it's fun to listen to the MP3s on the
You
Git.
know Ioannis Xenakis?
Yeah. Yes.
I think he is by far the single finest electronic composer that I know of.
Yeah.
What was that name again?
I should listen.
Ioannis Xenakis. It's Xenakis. He was Greek, but he lived in Paris much of his life or most of his life.
Yeah, and I haven't explored like his whole work, but it's like, I mean, a lot of his music, is mathematically inspired.
The first recording that I ever owned of his is covered with the white cover is covered with mathematical formula.
He's our man. Okay, I'm looking at this. Actually, there's not that much more. Okay, I can do this very quickly. It's just coming around year 7. So this is the last thing we'll talk about today, and then we'll pick up either probably 2 weeks from now, just because next weekend's July 4th. So as always, there's something that we've left out. Okay, you can take the square root of 2, fine. But what about you take the square root of -1? What's that supposed to be? Well, as always, you try to divide like 2 by 3. It's not an integer, so you add a new kind of number. It's a rational number. Fine, it's a fraction. Do the same thing here. If you want to divide by the square root of -1, that's just a new number. And we call it I, because at the time, when people started really seriously thinking about these things, kind of in the Renaissance, at this time, you could be rich and famous by solving, polynomials, solving equations out in public. Famous Italian mathematicians like Tartaglia and others, they would stage these mathematical duels where, like, in public, they'd compete to see who could solve this equation. And we're constantly spying on each other to see, what secret methods their competitors had developed to solve the equations. And, one of the things that came up was that it often happened that you would want to take the square root of a negative number, which seemed like not okay, but very often they would find like, well, by the end of the calculation, the I is like multiplied by another I, and then it's just the -1. So, maybe if you just use it in the intermediate parts of a calculation, it's no big deal. But we don't want to say like they're like real numbers, they're like imaginary numbers or whatever. But it really, they're really, really important. And it took a couple hundred years, but people eventually realized that they can be interpreted in a very simple geometrical way. You note, first of all, that there's this fourfold pattern. 1 times I is I times I is -1, -1 times I is -I times I is 1. So it repeats. And this suggests the interpretation of that multiplying by I is actually just rotating 90 degrees. Start at 1, multiply by I, get to I, multiply by I, get to -1, multiply by I again, you get -I, and multiply by I, you get back to 1.
So in fact, Matthew, I is not really a number, it's an operator. And in physics, it's a phase change of 90 degrees. It rotates your vector by 90 degrees. It's an operator, it's not a number.
Well, so I would say, I mean, like I would reserve the operator to refer to like, well, yeah, you could call it an operator. I mean, ultimately, it's a generalization of the idea of multiplication, right? So it's like multiplication stretches, but complex multiplication also rotates in the plane.
It's not an operator, it's a smooth operator.
Oh, can I steal that joke? That's
Go ahead.
so funny, I forgot to laugh.
So
No, really, what it really is a phase difference, you know, because e to the I
that's one very important way.
theta rotates the vector by theta. So and that's the sense I meant operator, as opposed to some calculational, you know, number.
No, totally.
Yeah.
Absolutely.
Because that's how it's defined in electrical engineering or in quantum physics or in, you know, that's essentially what it is.
Definitely. Yeah.
And because if you operate twice, you get -1, which is a 180-degree rotation. So just a single eye is half of that. It's a 90-degree rotation.
Yeah, absolutely. And so, you know, whereas we thought we were working with, I mean, this whole time we've been thinking about the plane, right? Like we got the square root of 2 by considering the hypotenuse of a triangle. We got the, you know, the diagonal proof going along the diagonal of this grid of numbers. And here it's, you know, affirmed yet again, the numbers at this stage of the game, once we add exponentiation and root taking into our repertoire, are in fact two-dimensional. They have a real part and potentially an imaginary part. And so you can think about them as little arrows living in the plane, where the real part is how much to go in the x direction and the imaginary part is how much to go in the y direction. You could also use polar coordinates. So you could write the point, you know, as r times cosine of theta, where theta is like the angle with the real axis, plus I sine theta. And you could also write it as r to the ei theta, r being the hypotenuse and theta being the angle. And there is a great proof about why that works, Euler's famous identity, but we will talk about that next time. The thing about complex numbers, though, is that what's great about them is that, yeah, like they're arrows in the plane, but they follow the rules of algebra. Like you can add, subtract, multiply, divide them, just like normal numbers. So, you know, when you add complex numbers, it's just laying the arrows end to end. Z plus W is the same as W plus Z. Multiplying complex numbers means to stretch the one by the other's length and rotate by the other's angle. So if you have r to the ei theta times s to the ei phi, it's just r times s times e to the I theta plus phi. And so, you know, like when you multiply, you know, a number by e to the I theta, what it does is it rotates it by 30 degrees. Finally, there's complex conjugation where, you know, you take a number and you basically reflect it across the real axis. A plus bi goes to a minus bi, or r to the ei theta goes to r to the ei negative theta. There's a typo here. What's the point of that? Well, there's a lot of interesting reasons, but first and foremost, look what happens when we multiply a complex number by its conjugate. If the complex number is a plus bi, we multiply it by a minus bi. We do our like little FOIL, we like da 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 da, and we get a squared plus b squared. So we can write the length of the hypotenuse of this triangle made by the complex number. In other words, like the length of that complex number as like a little arrow is just the square root of z times z conjugate. So it's, you know, undeniable or whatever. There's something actually two-dimensional going on. You know, initially we had a single pebble and we, you know, first, you know, had to agree on, okay, what's a pebble? Is the presence of the pebble significant? The absence? And then when we had multiple pebbles, we had to agree on where we start counting from. And then once we had the integers, we had to agree on like where 0 is, or is this positive, is this negative? And then once we had the rational numbers, we had to agree on like, oh, what's 1? My units of 1, your units of 1. We had a rational number to translate between their different denominations. But now at this stage, there's yet more context. We can agree on the angle between our axes. And that's just what a complex number does. You have two axes, one axis, another axis, what's the angle between them? It's just going to be some e to the I theta. And this allows us to translate between our different reference frames, for example, where the square root of 2 might be irrational here, but rational there. If we can take a diagonal line, which is, maybe it's like the square root of 2, we could just, rotate it by 45 degrees and now align it, with the real axis or something. Kind of switch around which one we want to regard as irrational. So we were talking before about, switching between reference frames. Is the grid system horizontal? Is it diagonal? Well, that's exactly what a complex number does. It allows us to switch between those different orientations. And then the final point to make is this, division by 0. Before, when we divided by 0 in the world of the rationals, we had a line and we wrapped it up into a circle. And here, what we do, we have the complex numbers. They live on a plane. And when we allow division by 0, the plane has a kind of infinite horizon. We imagine beyond each of those points, there's a point, and you get to the same point, no matter which direction you're coming in. And you're actually living on a sphere. And that point at infinity is just the point opposite to you, antipodal to you on the sphere. And we've talked about this before. You do the stereographic projection. This is one way of mapping every point on the plane to a point on the sphere. Here's the rule about it. If you do it from the South Pole, we'll find that it's very useful to do it from the South Pole. If you have some complex number or infinity, you can get the XYZ coordinates with this little expression, or if it's the South Pole point, you got infinity. And similarly, if you have your XYZ coordinates, you can convert them into a complex number or infinity, just like this. And so we discover that at this stage, what are the numbers? We had pebbles, we had counting numbers, we had integers, we had rationals. And now we have what? Ultimately, points on a sphere, which pick out a direction in 3D space. And final thought is that, this stereographic projection, we've been talking a lot about ancient stuff. It was in fact known to Ptolemy, and it's related to, the gnomonic projection, which is like the theory of sundials. You sort of imagine you got a stick in the ground and the sun comes up and it casts a shadow, which initially is in some ways of infinite length as the sun comes up over the horizon and then shrinks down here and then traces a path like this. The stereographic projection preserves angles, unlike Archimedes' favorite projection, the cylindrical projection, which preserves area. And we'll talk about next time, its relationship to Mobius transformations. And as you can see, we have finally reached the sphere. And so next time we will begin by talking about spin. So there you go. We got through 5 whole sections. Thank you guys so much.
It's interesting that you ended on Ptolemy because around in the 1st century BC, he approximated pi as 3.1416.
Not bad.
Matthew.
Not too shabby.
Not too shabby, yeah.
Matthew, this mnemonic projection sounds like it's conformal. It preserves angles. Are you going to be getting into conformal theory at all?
We will talk about conformal transformations. We won't be talking about like conformal field theory in any detail.
Yeah, because we're getting into that a little bit in the New York quantum meetup. Moshe, who was on, leads that meetup. It's tomorrow at 2 p.m. You're all welcome.
Yeah, no, I'm going to try to be there.
And I just, wanted to say that, complex vectors, I don't know if you're going to get into this, but quantum mechanics is based on Hilbert spaces. And a Hilbert space is really a bunch of orthogonal complex vectors. Could be an infinite number of dimensions.
The starting place for next time is this. well, if we can make a pile of if we could join pebbles into a pile, what if we had a bunch of complex numbers? We could join them into a quote unquote pile of complex numbers. Well, what's that? It's a polynomial, and the complex numbers are its roots. And polynomials are functions from the complex numbers to the complex numbers, generally speaking. And they have a natural basis, which is formed by monomials. And that's exactly where we're going to go next time. Polynomials, vector spaces, and eventually, the idea of a Hilbert space. It's exactly what we're going to do, definitely.
When is the next lecture?
Probably in 2 weeks, just because next weekend is the July 4th weekend.
Is it going to be on a Saturday or a Sunday?
If Saturday works for people, I'm down. Moshe a couple weeks ago asked if I could move the Brooklyn stuff to Saturday, just as not to interfere with his stuff. Which,
he does it.
Me.
I'm sorry, he does it Sunday at 1 p.m. I think I said 2 p.m. It's tomorrow at 1 p.m. That's when he does it. Yeah, Saturday.
It works in a COVID epidemic.
Yeah,
What was that? Why?
Saturday works in a COVID epidemic. Otherwise, no.
I don't get the joke. What is this? Some kind of dark humor?
They'll have a lot of free time, which is good.
Thanks, Matthew.
Yeah, it's any other questions, or if not?
I just had a kind of a closely related but semi-random thing. So there was a document. I'm not the type to try to push a lot of documents that I think are really cool on people because it's just hard to deal with people doing that to you. But so I'm really selective. But there's one that I thought was, if you haven't seen it before, it's really awesome.
Yeah, send it, please.
And but at the same time, I was gonna post it as like a link, but then I feel like that looks shady, just like a link, because it wasn't even HTTPS,
Yeah.
So I'm just wondering, like, maybe have you heard of this thing? It's this Xavier conference. It's a transcription of the talks and the conversations between the attendees. It was like in 1962 or something like that. And it's got like Dirac and Aronov and Wigner.
No, that's fascinating.
And it's the only thing I know of where it's actually physicists, high caliber guys talking to each other about foundational interpretation.
Wow.
And so it's interesting about like to see what they think, but also to see how they talk to each other. Like, do they like cut each other off? All that kind of stuff. And Wigner is much, because you mentioned last time about von Neumann and the the psychophysical parallelism.
Yeah, we'll come back to that, by the way. Don't worry.
Yeah, so I want to give this, I don't know, maybe be utilized, but Wigner's, his take on the role of consciousness is made pretty explicit, but it's an interesting.
It's great to be able to peek, in a way, behind the curtain of like the Pythagorean, brotherhood or sisterhood. It's like, it's still true today. I mean, ultimately, just because science has a language of its own, that, the way it's presented to outsiders is not always the way that, insiders talk amongst themselves about it, like especially as regards philosophy, just because, things are open to misinterpretation.
Contemporary physicists are less willing to talk about foundational stuff because it's too risky professionally, and there's a sense of, if they haven't already thought of it, I'm probably just going to sound stupid. But so these guys are not.
Like the Cold War context, everyone was like real paranoid.
But it turns out that actually because I was trying to find a less shady looking URL that hosted it, and the one that I did find.
Don't worry about it, Michael.
Okay.
Well, if it's a PDF or something, I can
host it. Reward for making that effort. That concern was that I discovered it's hosted on, I think it's a UC Irvine site, and there it has a whole archive of Hugh Everett scanned handwritten notes, not to endorse or not endorse his theories, but like I love historical stuff like that, just for its own sake.
Better than Hugh Everett's Many Worlds. And I gave a presentation last week, but Moshe is going to continue tomorrow on David Bohm's interpretation of quantum mechanics, which is a much more intuitive and physically intuitive interpretation of what's going on than the Copenhagen interpretation that they teach in school.
Well, click around, because actually there are some letters, not that many, but there are some actual correspondences between like Bohm and Everett on this same.
Yeah, but Everett, I got to tell you, Everett is fantasy. I don't think any real physicist takes that seriously. It's fantasy, and again, it can't be falsified. You know, it violates Karl Popper's theory of what science actually is. But there's another comment I wanted to make. You mentioned Wigner. Wigner was wrong about a lot of stuff. And what amazed him is that, and it also amazed Einstein, that we could even explain how the universe works in any degree of accuracy. But what I want to say, and this is a trap that a lot of scientists get into, math is not science. Some math can approximate a description of the real universe, but math is not science. Math is something we invented in our brains to try to figure out a way to describe what we see in the real universe. And whatever physics theory you have that's described by math, so-called language of science, whatever physics theory you have is only an approximate theory. There is no exact theory.
Are you referring, is he the one that wrote that article on like the unreasonable power of
right, that was the unreasonableness of
unreasonable effectiveness,
whatever. And this was Einstein's belief too, that it was amazing that we could even attempt to describe. But again, math is not physics. Math at best is the way we have formulated math is at best an approximation to what goes on in the real universe. And when we talk about irrational numbers and approximations and probabilities, this is not the way the universe works. And Bohm, by the way, Bohm did away with these probabilities that the Copenhagen interpretation famously, and people believe it. Scientists and lay people alike believe in this probabilistic nature of nature. And it just isn't so. Read Bohm. Google it. B-O-H-M.
Take a look also at the article in the Times. I'm not even sure if it was.
I know what you're talking about. Yeah, that's
last few days about Angelo Bassi's objective collapse theories. I think you will be.
New York Times magazine.
Quite fascinating.
It is complete bullshit. The guy doesn't know what he's talking about. He's making the mistake that I just indicated. He's first of all, he's looking for what Einstein was looking for, hidden variables. And John Bell disproved there cannot be hidden variables.
We'll talk about that.
There cannot be hidden variables.
I disagree
quantum theory
immensely.
I disagree. Yeah, well, next time we'll talk about, we'll talk about these issues, probability. I mean, I incline, more to the Copenhagen kind of interpretation in some ways than not. But we'll definitely, problematize that.
I'll post this link, and I do recommend you look at it. I'm terrible at writing these little blurbs to motivate why one should click on the thing. So if you just take my word for it, because I'll just spend all day trying to think of a nice, concise.
And this Michael, this was a conference that Wigner and some other people attended.
Yeah, at Xavier College or University, and actually I think the organizers were Rosen and Podolsky of the P and the R.
The EPR thing.
Yeah, I mean, so it's got,
And this is a video that was recorded?
No, it's there. I think they actually had everything audio recorded and it was transcribed. But then they also had an agreement with the participants that they would all be given a chance to edit, so that they wouldn't worry about saying something and then regretting it. That they'd all have the right to edit the final draft of the thing. But you see actually the crossouts in this version. You see the crossouts and what was written instead.
That's funny.
Was Pauli, do you know if it was Pauli there? Because Pauli was famous for shooting people down at these conferences.
Yeah.
Even when he was wrong and they were right, he would shoot them down and they would sit down and not say another word.
Wigner and Dirac are the only two sort of, you know,
Dirac,
that generation there.
Dirac was Wigner's brother-in-law. Dirac was
Really?
married to
Wait,
Wigner's sister. Little
I didn't know
known historical fact.
Anyway, Matthew, thank you very much for the session. I have actually sunk down to 158 pounds, which I haven't weighed since I was 15. So I'm going to eat, but thank you.
Matthew, did you post this? Matthew, is this posted?
The notes are posted, and I'll post this video by the end of the night.
Okay, great. But the document is already posted.
Yes.
And so just last thing, is the best place for me to put this link on a message board posting? Is that the right place for it?
Yeah, you could post on the message board or like leave it as a comment.
Okay.
The Brooklyn Quantum site, or whatever you want to do, or I could even, if you email it to me, I could put a link to it like on the intro page.
I started off by doing that, and then at some moment it said like this organizer does not accept messages.
Really?
But,
okay, I'll look into that too, man.
Yeah, whatever. I'll just post it in, whatever.
Cool.
Mm-hmm.
All right. Thanks.
Well, it was great talking to you all, and until next time.
Ciao.
Bye.
Oh.
Right.